Show Bay is here. Is not here? Okay, we will check if he's in remote, otherwise we will have another presentation that time. So I think we can already welcome the presentation by Malena Rice. She is the PhD prize of 2022. So please, Malena, can you come? And I'm very proud to give you the certificate. So, congratulations.
Thank you so much for the introduction, and thank you all for being here. It's really an honor to join and to get to talk about my dissertation that was called A Dynamical Synthesis of Planetary Systems. So since defending my PhD, I've actually had two career changes, and I'll be talking about some of the work that I've done both in my dissertation and beyond. So I wanted to kind of give some context for that. Mention that I got my PhD in 2022 at Yale University. And since then, I did a year as a 51 Pegasi IB postdoctoral fellow at MIT, picked up some collaborators along the way, and then I ended up Oh, there we go. Okay, great. Well, I didn't get terribly far in, but I'm now back at Yale is sort of the yeah. So I've been at Yale for most of my astronomy career, and I'm back, and I'm really excited to have had the opportunity back at Yale to have started building my research group. And so these are just some of the wonderful people that I get to work with. Some of the kind of continuations upon my PhD dissertation have been led by this awesome group. And this has been sort of the great joy of the past year, has been getting to work with all of these wonderful young students and postdocs. So sort of the big question that I've been addressing throughout my PhD as well as beyond is what underlying mechanisms produce the broad diversity of observed planetary systems. And I approach this from a dynamic standpoint. So I'm interested in how planets, stars, and minor planets interact with each other in order to kind of shape the physics that actually forms our planetary systems. So this is the 6 papers that comprised my PhD dissertation. I'm not going to have time to talk about all of this in depth in 20 minutes, so I'm actually just going to focus on this bottom row here. And I'll talk a little bit about some of the work that I did in my PhD, as well as some of the extensions that have come out of this. So I'll start with the first of these, which is using the Transiting Exoplanet Survey Satellite, or TESS, to study the solar system. And TESS was not really designed to look at the solar system. It was designed to look for exoplanets around stars that are in the solar neighborhood, with the idea that with those exoplanets, you can study their atmospheres and other properties up close, since they're around relatively bright stars. But it turns out that TESS also just stares at each point of the sky for about 27 days at a time, and there's a lot of other science that you can do with it. TESS is fully open source. All the data is publicly available, and so anyone can just download it and take a look through and do whatever science you'd like with it. There's lots of supernova and other kinds of science as well. So what I've been doing with TESS is trying to understand what we can dig out from the noise of the objects that we have not yet discovered in the outer solar system. So what might exist within this data set that we're just not looking for with kind of the automated transiting exoplanet pipelines. TESS has looked at, this is just showing kind of the initial primary mission. TESS has looked at something like 95% of the sky at this point, and it's getting pretty close to 100%. It will be at 100% probably within the next 2 years. And with TESS, if you, instead of actually looking at the stars, go ahead and subtract out all of your stars, and you subtract out all of the sources that you actually know of already, then you can start looking for other things that might be hidden within that noise. So in my dissertation, I developed a pipeline where I said, okay, we're going to get rid of the stars, we're going to get rid of all the stuff that we know about, and then we are going to shift and stack these images along the paths of potential distant solar system objects and see what kinds of detections we can get from that. So this is just showing an example of what this looks like when you're recovering one known distant extreme trans-Neptunian object. This is a relatively famous one named Sedna that was sort of part of the deposing of Pluto back in the day. And so Sedna is pretty faint. It's about V equals 20.6. And what we're seeing here is on the left, just an image that is a frame of TESS where we've masked out all of our stars, we've done some background subtraction, and you're just seeing asteroids that are passing through the frame. And then on the right, we're shifting and adding together these images along the path of this very faint, distant outer solar system object, Sedna. And you can see when you're close to frame 0, there is very little signal, but as you add together hundreds of frames, you can actually pull out these extremely faint objects that are otherwise not detectable in any of these individual images. This paper from 2020 was a proof of concept that was just showing this is something that we can do, not only if you know where the object is, but also in the middle and right frames here. If you don't know where your object is and you conduct a blind search and you just shift and stack your images along everywhere in the sky that you could possibly have an object, then you can also actually blindly detect some of these faint distant solar system objects without actually telling your algorithm where they are. So the idea here is you just shift and add together the images along all paths that are of interest, anything that could be realistic, which in the outer solar system is really just linear paths because these objects are they're very slow moving. So the Earth is actually moving past that region of the sky more quickly than the object is moving. And we're just looking at parallax motion at that point. So you just get sort of linear paths within the TESS image. So in addition to this initial proof of concept work, I've been working with this awesome group that's listed out here to develop a more general outer solar system detection pipeline. So there isn't a lot of a framework for TESS solar system science just yet, but this is something that could be really lucrative if we search through these years and years of data that have been collected since 2018 when TESS started actually collecting these data. So the idea here is that we want to actually extract these objects that are below the single frame detection limit at scale. This is kind of an overview of the general idea of our pipeline. We have at least preliminary pieces of all of these pipeline components put together. And these are kind of a more general, you can apply this to any point of the sky type of pipeline. So you have to sort of account for different scattered light in different parts of the sky that's observed by TESS. And so here's just for a proof of concept of one of the objects that we discovered, which we believe is TESS's first discovered object in the very distant solar system that's actually been confirmed with ground-based follow-up. We go ahead and we take a look for any of these objects that are really high signal to noise. We make sure that the signal is actually accumulating linearly. So that's what's in this top right panel here. And then we go on the ground and we say, well, you're going to get at least some false positives with the TESS detection method. And so you actually have to go to ground-based telescopes and follow up these objects. So this is something that we've been putting together the infrastructure to be able to do at a larger scale that's being led by Ben Cassess, a PhD student at Columbia who's working with me. I wanted to mention we find some other fun friends in TESS. So I've had a couple of undergraduates working with me over the past summer to also look at the light curves of Uranus on the left and Neptune on the right. So the movies are kind of jittery here, but you can see that there are these bright objects that look like stars and they just move through the path of the frame. And it turns out that we have about 2 to 3 months of data for each of these planets where we can look at the light curves in great detail and understand without any gaps in the data, since TESS is a space-based spacecraft, we're able to actually study those light curves with pretty tremendous temporal precision. All right, so that's this first component. And for the rest of the talk, I'm going to turn to exoplanets, which has been a pretty big theme in my research more recently. There are 2 different talks or sort of papers that have come out of this from within my dissertation that I've extended on a lot over the past couple of years. And these are both looking at this idea of stellar obliquities. So trying to understand how orbits are oriented in exoplanet systems. So they came out in this order, but I actually started with this project on the right first. And, research is very nonlinear, so it ended up coming out significantly later than the first one. But I want to start by talking about this paper on the right because it really was the motivation for the work that is shown on the left as well. So just to situate everyone, the stellar obliquity, which is the angle that I'll be talking about here, is just a measure of whether the orbit of your planet is going in the same direction that your star is spinning. So you can have a planet that is orbiting the same direction of your stellar spin, or it can actually be misaligned with your stellar spin. If we look at our solar system, it turns out our planets, they're pretty nicely aligned with each other in terms of their orbits, and they're actually slightly offset from the stellar spin or the solar spin within the solar system. So it turns out there's a slight tilt between the orbits of the planets and the spin of the sun. It's about 6 degrees. And this is a relatively small tilt, but when you look at exoplanets, there are lots of planets that are on sideways and backwards orbits that have been seen for these gas giant, often hot Jupiter exoplanets. They are very often not nicely aligned with the spin of their host star. And this could be really important for understanding how those planets form and what makes them so distinct from the solar system. We're seeing lots and lots of exoplanet systems that are very unlike the solar system. So this is something we can measure amazingly. It's a very small signal through something called the Rossiter-McLaughlin effect. So if you have a transiting exoplanet, if it passes in front of its host star at some point, your star actually also spins. So it has a blue shifted side and a red shifted side, a side that's moving towards and a side that's moving away from you. And if your planet is blocking out the blue shifted side, your spectrum will look slightly redder, and vice versa if it's blocking out the red shifted side. And what this ends up looking like is a perturbation to your radial velocity profile. So you get this kind of wide radial velocity profile. If it's a circular orbit, it looks like a sine wave. And then on top of that, if you have a misaligned orbit, then as the planet transits, you get a little warp that is sort of asymmetric, or if it is kind of going in the same direction as your host star, if you block out the red and the blue for the same amount of time, then you end up with a symmetric signal here. The equation here is just showing the amplitude of the signal, and the main takeaway from that is really just that we're really biased towards big planets that have deep transit depths, which means that most of these measurements have been made for hot Jupiter planets. So if we want to figure out what actually causes these misalignments, there are a couple of different ways that you could do this. I'm focusing on hot Jupiters because, again, that's where we've gotten most of our measurements. And you could either say, okay, well, if we've got a tilted protoplanetary disk, and then you just form planets in a tilted disk, then you can get a misaligned planet. That's one option. Or you could have something that happens after your protoplanetary disk disappears. So common ways that you could do this that are sort of theorized in the literature are you could have planet-planet interactions, some kind of scattering event that could launch one of your planets on a highly eccentric orbit, and it tidally inspirals every time it gets very close to its host star. Or you could have something similar happen if you have a companion star or something else that is perturbing your system. So kind of the two categories here are either you tilt your system before your disk goes away, or you tilt your system after your disk disappears. So if we I skipped a slide. If we take a look at all the hot Jupiters that have these measurements so far, this is measured by lambda, where lambda equals 0 is perfect alignment. Lambda equals 90, you can think of as roughly polar, so sideways orbits. Lambda equals 180 is sort of like a backwards orbit. The systems look like this. We have a couple hundred measurements at this point. And you'll notice that I distinguished between the blue and the red points here at something called the Kraft break. So the Kraft break is just a rotational discontinuity. So above the Kraft break, your stars have radiative envelopes. Below the Kraft break, they have convective envelopes. And about 15 years ago, it was found that if you look at the hot Jupiters that are below or around stars below the Kraft break or above, then they show different patterns. So the hot Jupiters around very hot stars are often misaligned, and that's not true for the ones that are around cool stars. And because this transition happens around the Kraft break, it was then thought that maybe this has to do with tides in some way. So it may be that you actually start out by misaligning lots of hot Jupiters, but the ones that are around the cool stars are easier to realign over time, whereas the ones around hot stars may just retain their misalignments for a long period of time. So if we want to actually tie this back into hot Jupiter formation, then eccentricity really helps us to understand how to put this all into context. Because if we think back to the sort of either you form within the disk and it was misaligned in the first place or afterwards, if you form in a misaligned disk, then you would have no reason to expect any relationship between misalignment and eccentricity. Whereas if you have this high eccentricity migration that is commonly postulated as a way to form hot Jupiters, then you would expect that the systems that are misaligned might also be the ones that are more likely to be on eccentric orbits. So this is just showing kind of a schematic of a comparison between lambda for the hot Jupiters on eccentric orbits that are in purple versus the ones that are on circular orbits in gray. And sort of the main takeaway here is that the purple line looks like it follows a roughly linear trend. There's no obvious distinction below and above the Kraft break. Whereas when you look at the circular orbits and take the cumulative sum of those values, then you end up with a very shallow increase in lambda, the cumulative sum, that then increases after you hit the Kraft break. So another way to look at this is you can just distinguish into the high eccentricity versus equals 0 orbits and hot versus cool stars. And you can see that if you're on eccentric orbits, then you follow roughly the same probability distribution of your misalignment, whether you're around a hot or a cool star. Whereas it's just this purple line, the E equals 0 around cool star systems that show this very strong trend towards lambda equals 0, which is spin orbit alignment. So what we're seeing here, just to kind of put this into easier to understand terms, is hot Jupiters around cool low mass stars are usually aligned, and around hot high mass stars are often misaligned. And this has been known for a long time. And what we showed in this work is that if you add this extra quadrant of eccentricity, this trend is not actually evident when you look at hot Jupiters on eccentric orbits. It's just this one quadrant where we're actually seeing a lot of aligned hot Jupiters. And this actually fits in really nicely with this idea of tides affecting the systems. So if we look back at this figure where we distinguish between high eccentricity, low eccentricity, hot, cool systems, if you just take these lines at the bottom and take some mixture model of these gray models that are the outcomes of what you would expect from high eccentricity migration. And then you apply a tidal model to them. This is a very simple equilibrium tides, probably oversimplified model, but just to get a first order sense of whether this idea works at all. If you apply that model, then you actually end up with, over the course of several billion years, a pretty good match to the purple distribution. We don't expect them to perfectly match because the purple distribution only has about 5 points beyond lambda equals 35 degrees. So the tail's not very well defined, but you end up with the same peak towards 0 is the main point there. So this really seems to be pointing towards dynamically violent hot Jupiter formation because we're seeing that the eccentric systems are often also misaligned, and there does seem to be some relationship between eccentricity and obliquity. So this then brings me to another way that we can approach this question, which is looking at more of these spin orbit measurements. So I noticed, together with a couple of collaborators, that if we take a look at the planets that are around hot stars, but are on slightly wider orbits, remember that the hot Jupiters around hot stars are often misaligned. That doesn't seem to be true if you look at wider orbital periods. We notice that there are quite a few that are aligned, and we actually didn't see any that were misaligned. So we said, okay, we're going to go out and we're going to take more of these measurements and figure out if this is actually telling us anything insightful or if this is just small number statistics. So we started the Stellar Obliquities and Long Period Exoplanet Systems, or SOLS survey. And it was really focusing on warm Jupiters because we happen to be also at this wonderful junction where the TESS survey that I mentioned for solar system observations, but that's also detecting exoplanets, it happened to be finding a lot of these warm Jupiters. And so we were able to get more and more of these measurements for these wider orbiting planets and to actually fill in this gap where the warm Jupiters we don't expect to be as affected by star-planet tides. It's easier to actually interpret if a warm Jupiter is aligned. It probably formed aligned. There's no way that it could interact with its host star on short enough timescales to actually realign it within the system lifetime. So this is just showing 10 of the observations that we've collected. We actually have 19 at this point, which is something that I'm really proud of. We've had a couple of undergraduate-led papers that have come out of this survey as well. And we found a lot of really interesting things. Since I'm kind of low on time, I want to just highlight maybe one and just highlight a couple of the great students who have worked on this survey. So probably the result that I'm most excited about is this one, which is that in single star systems, we're finding that it is actually true that the warm Jupiters are aligned. We've never found a single warm Jupiter that is actually misaligned if it doesn't have a stellar companion in the system. So that's these pink points that are to the bottom right, whereas you see the hot Jupiters, even in single star systems, you've got a lot of them that are misaligned. This is true even when you have hot, warm Jupiters on really eccentric orbits of 0.4, 0.6, 0.8 even. So this is something that was shown by an undergraduate student working with me, that as you collect more and more of these observations, you can see that they're still aligned. Even if they're on extremely eccentric orbits. And then another collaborator, Shan-Yu Wang, who's a postdoc at Indiana University, showed that this is also true when you account for stellar host biases. So I mentioned hot Jupiters are often misaligned around hot stars, but not cool stars. And we still find, even when we collect more and more observations around these hotter stars, that they're all spin orbit aligned. And so the takeaway there, I would say, is actually that the hot Jupiters are forming in a very different way. They are forming in a dynamically violent way, and there's something that's happening after the system has formed, so after the disk has dispersed, that's actually causing these spin orbit misalignments. And the reason for that is that you would expect the warm Jupiters to be aligned at the same rate if you were just tilting your protoplanetary disks. There's no reason that hot and warm Jupiters should form in differently tilted types of disks. So since I'm low on time, I'm just going to run past a couple of these and end with my conclusions. And thank you all again, and I'll take any questions.
Malene, are you? Okay, wonderful presentation. Do you have a very short question? We have just one. Okay, go ahead.
Yeah, thank you, Melinda. That was a very nice talk. Can you give us a little bit of context on what you plan to do in the future? There are several space missions and also ground-based opportunities. Can you say how you could use all of that to improve your theory?
Yeah, so we're continuing to take more of these spin orbit measurements. So that's something that as we discover more planets, it's possible to start looking at smaller planets and see if they follow similar trends. A slide that I skipped was actually mentioning that we're starting to look at brown dwarfs. So there are very few systems that have known spin orbit measurements for brown dwarfs, and to try to understand if those form similarly to planets. And I know there's some other folks who are doing some great work in this space as well. And I'm also really excited about some of the upcoming missions. I think it would be probably slightly a pivot, but not too much. I have worked on a bunch of stuff, and I'm just really excited about learning about exoplanets very broadly. And so I think there are actually a lot of opportunities with the NASA Roman mission, the Habitable Worlds Observatory, but that is NASA's next flagship, is something that I've gotten involved in. And I think there are a lot of ways that we can progress each of these directions that I'm happy to talk about in more detail as well.
Yes, thank you. There's also the Plato mission, and there's the Ariel mission and other missions that will help us characterize some of these planets.
Yes.
Thank you.
Yeah. Thank you.
Okay, thanks again. We can move to the next presentation that will be in remote by Vardan Elbakian. He is on the dust growth and bubble formation in the initial stages of protoplanetary disk evolution. Okay, you can start.
You need to unmute.
Yes, sorry. Hello. Yeah, can you hear me?
Yes, perfect.
Yeah, thank you. I would like to first thank the organizers for this opportunity to give the talk, and yeah, hope that you can see my slides. So after the nice talk of about the observational perspective about the planet, I would like to present some theoretical perspectives about how these planets are forming and at the very early stages of planet formation. So I will start from the very beginning when the molecular cloud is still collapsing, and some simulations are showing that that during this initial stages of the formation, the dust particles grow until a few tenths of micrometers in this envelope, and could already be quite large already in the envelope. And some observations, not the theoretical studies, but the observations are showing that even larger particles, a few hundreds of microns or even millimeter sizes, they can exist on the scales of a few hundreds or thousand of AU around this new forming protostar. However, some theoretical simulations, some hydro simulations are showing that these dust particles are growing to a few hundred microns very quickly, in a few hundreds or 1,000 years, which is relatively quick, but they are growing in the very central part of the collapsing molecular cloud. So this brings us to another conclusion that possibly these large particles could be ejected from this from the inner part of the forming protostellar molecular cloud from the disk, and can be ejected. Why it's also important? Because although this dust is only like 1% of initial mass of the total molecular cloud, one could say negligibly low, but this 1% can play an important role. One of the examples is like the sizes of the disk could be different during the formation when you have different dust to gas ratios, or it can also impact the magnetic field, which can later impact the evolution of the disk. So so dust particles are playing a very important role in the formation of the disk. That's why it's important to study the dust already in the envelope. From another important thing is that as we all know, that planets are forming around very young stars. Already in class 0, class 1 stages, when we have just formed protoplanetary disks. We can see some ring structures or gaps around the central protostar inside the protoplanetary disk, which are probably most probably because of the formation of the planet already on a few in objects of a few 100,000 years, which is very early. So this is another conclusion, that we need to study the disk evolution from the very beginning, from its start. So what we've done is 2D, first of all, is 2D hydro simulations, global simulations of the formation of the disk from the very early stages of molecular collapse. molecular cloud collapse. And what we found, first of all, is that in a very young protostellar disk, dust particles are growing until a few centimeters in size after a few thousand years. So they present in the disk after a few thousand of years of after formation of the disk, and most of all because of the constant supply of the small particles from the envelope around the disk. These dust particles are present in the disk for about like 1 million years. So you have like millimeter or larger centimeter size particles in the disk for 1 million years. Which is observationally proved. We have many observations of a disk with centimeter and millimeter dust particles, which are a few 100,000 of years or even older. I have no time to go, unfortunately, to the details, so I will skip the details and jump to the next stage of our simulations with our new generation code with it's a 3D code with nested grids, and we try to do the similar simulation with the initial cloud collapse of collapse of the molecular cloud, starting from the very beginning, and what we see now, that how the disk is forming and evolving. Unfortunately, we cannot do the simulations for that long as in 2D, like not million years, but first a few tens of thousands of years are simulated, and what we found that the dust to gas ratio in the disk is highly non-homogeneous. So it is larger than like conventional value of 1 to the 100 in the mid plane, and but it's a highly non-homogeneous. Some regions are much higher than this conventional value. Some regions are even lower, but in average, this value is staying in the mid plane. Another important thing is about the dust settling, the vertical settling, because of the perturbation from these spiral arms that are forming in the protoplanetary disk. The dust is steered up, and the vertical scale height ratio for the dust to gas ratio is between 0.2 and 0.5, which is not that high, but also is showing that the dust is not totally settled in the mid plane. So there is some steering going on, and this is because of the gravitational instabilities in the disk. Another important thing that is confirming our earlier results from 2D simulations is that in the very early stages of the protoplanetary disk formation and evolution, we have already centimeter-sized particles in the disk, but because of the low Stokes numbers, there is these particles are not well connected, are not disentangled. They are well collected to the gas, and we don't see a strong accumulation of the dust particles in the spiral arms. We see more accumulation of the dust closely to the spiral arms and even in the regions between the spirals, but there is no strong accumulation of the dust particles in the spiral arms. Regarding the pebbles, these large particles above 1 millimeter that have Stokes numbers larger than 10 to the -2, we again see some non-homogeneous and patchy distribution inside the disk. These particles are absent in the inner 10 AU region because the Stokes numbers are really low in that region, and but we see that pebbles are strongly concentrated in the mid plane. So the large particles are settled down in the mid plane, and at the same time we see that if we measure the total mass of the pebbles in the disk, we see that about a few tenths of Earth masses are already in the present in the disk as a pebble, which is more than enough to form a protoplanet. At least if there was a start of formation of protoplanets through the pebble accretion, for example, or if there were some instabilities like a streaming instability present in the disk, the planets would already start form at these very early stages of the disk formation. So this brings me to my main conclusion that the dust is growing very rapidly in the protoplanetary disks to the pebble sizes in a very early stages. The one thing that I have no time to discuss is that turbulency is very important for the pebble formation, and in very turbulent disks, less pebbles are formed because you don't have this chance to grow. So very early disks already have enough pebble mass to start a planet formation, and this is very important to have a chance for the multidimensional simulations to capture all the dynamics in the present in the disk to have a general knowledge how the disks are forming and how the dust is evolving inside them. So yeah, and this is all, and I would be happy to answer all your questions if there are some. Thank you.
Thanks a lot for the presentation. Questions in the room or remote?
Hi, thank you for the thank you for the presentation. I had a question when you're running your simulations, it looked like the particle size was not going past a couple of centimeter size scale, and it looked like it's kind of stuck there. And so I was wondering, is this because it wasn't running long enough, or is there something that's preventing the particle size from becoming larger than centimeters? And how do we
actually, yeah, that's a really good question. Yeah, so there is such a thing as like it's a theoretical barrier, of course, it's a fragmentation barrier. So this is the size above which the particles, for example, when you have like a collision, they are not sticking with each other, but they are fragmenting each other. So as you can see on the animation, I hope. After this centimeter sizes, the dust particles are starting to fragment each other when they are colliding. So basically, this is the reason why we don't have like larger particles.
Do we get bigger ones?
Yeah, why we're not getting bigger ones? Yeah.
Thanks again, but we have to move to the next presentation. Thank you. By Amina Diop on constraints the gas mass of protoplanetary disk. Okay, you can start. Thank you.
Yeah. Good morning, everyone. My name is Amina Diop, and I'm a PhD candidate at the University of Virginia, working with Dr. Ilse Cleves. And today I'll be talking about my PhD work, which aims to constrain the gas mass of protoplanetary disks. Green, okay, thank you. Yeah. So as my title shows, I work on protoplanetary disks, which are these disks of dust and gas and ices that surround young stars. And these are important systems to study because this is where planets form. And now that we have observed a wide diversity of planets in terms of chemical composition and orbital patterns, it's very important to understand how disks evolved to give rise to this diversity. However, we have one challenge when it comes to protoplanetary disks. It's very challenging to measure their gas masses. And this is due to the fact that the bulk of the disk is made up of molecular hydrogen, which cannot be readily detected in these systems. So to overcome this limitation that we've had, we've used CO as a mass proxy, and this is due to the fact that it's the second most abundant molecule. It's readily detected, and it has a relatively simple chemistry in the interstellar medium. But surprisingly, when we use CO to derive gas masses, we find them to be very low in general, and in most cases below 1 Jupiter mass, suggesting that these systems are not massive enough to even form a Jupiter mass planet. And this is when we assume an ISM CO to H2 ratio of 10 to the negative 4. But when we look at another molecule, that is hydrogen deuteride or HD, we find a different story. So for the 3 disks for which we have HD data with Herschel, we find masses that are 1 to 2 orders of magnitude higher than masses that are based on CO. And this discrepancy between CO and HD is suggesting that disks are not as gas poor as suggested by CO, but rather some processes are impacting CO chemistry. And so this discrepancy has pushed us to revisit CO chemistry and figure out what's happening in these systems. So some studies have found that CO can be chemically processed into more complex species, and that this level of processing depends on the physical conditions that we have in these systems. And these studies have investigated this question using a full grid of 2D chemical models with varying disk and stellar properties. But this can be quite a computationally expensive approach and also very modeling extensive. So as part of my PhD, the first project that I explored was seeing if it would be useful to complement our chemical modeling efforts with machine learning techniques to better explore our large model simulations and better unveil the relationship between physical conditions and chemistry. And so specifically, we explored how CO is impacted by the disk physical conditions, and that is the gas density, gas temperature, cosmic ray and X-ray ionization rate, and UV flux. So of course, for our machine learning approach, we need some data. So instead of using a large grid of full disk models, we just focus on one model. Since already in one disk, we already have gradients in the physical conditions as shown in the figure here. So our data set is made up of this set of individual points that make up the model. And after data cleaning, we end up with around 3,600 individual data points. And then in terms of the machine learning approach, so our goal here was trying to understand how all these different physical conditions affect CO. And so we wanted to build a good predictive model, but also an explanatory model that allows us to understand how the physical conditions impact CO chemistry. And so it made sense to start with the simplest algorithm that we have with machine learning. So we worked with multiple linear regression and polynomial regression, which have the mathematical forms shown here, where Y is our dependent variable, which is a CO densities that we extract at 1 million year, and the X values are our independent variables, which are the physical conditions. So specifically, what we were looking at were the A and B values, which are the coefficients, which tells us the importance of different physical conditions, and their signs tells us whether they destroy CO if they have a negative sign or help preserve CO in the gas phase if they have a positive sign. So after conducting a detailed study, I don't have time to go through all the steps, but we found that for our single disk model, it's best fit by a simplified polynomial model. And what we mean here by simplified is a polynomial where we take the 10 most important terms to remove correlation between independent variables. And this figure here is showing the coefficients of the different terms that are in that polynomial. So just looking at it right away, we find that the gas density terms are the most important terms, which makes sense since we expect the amount of CO in the disk to scale with the amount of gas that we have present. We also find that the gas density and the gas temperature terms are the ones that appear the most often, and it makes sense since the gas will set where CO is in the gas phase or in the ice phase and where it can be transformed into other molecules. And of course, the gas density is proportional to the amount of CO. We also find that cross terms are important, suggesting that physical conditions act in concert to affect the chemistry of CO. And when we compare our negative terms that are remaining after removing gas density terms to the positive ones, we see that the negative side tends to slightly dominate, which is suggesting that the processes that are reducing CO in the disks have a slight upper hand on the ones that are maintaining CO in the gas phase, suggesting a tendency toward depletion, which is consistent with what we observe about CO. I also have some additional results, but I cannot share everything given the limited time, but we also find that warmer temperatures prevent CO from being turned into other species, while a high cosmic ray ionization rate helps process CO into other species. So all in all, through this study where we use a machine learning framework, we find results that are consistent with the previous studies that use this large grid modeling approach that show that machine learning techniques can be helpful to help us understand how physical conditions affect chemistry. And also this is consistent with the fact that we see that we have challenges just using CO as a gas mass tracer because it's undergoing so many different processes. And if you want to go into more depth, you can talk to me or you can also check out the paper. So I mentioned earlier, we have also used HD as a mass proxy, and we find that it's giving higher masses, but HD can only be detected in the far infrared, and we don't have any facility that can currently detect it. So the question is now, given these challenges that we have with these molecules, what is the way moving forward in terms of determining disk gas masses? And this is where multimolecular approaches come in. So some recent studies have found that when we combine CO line fluxes with N2H+, we get disk masses that are 10 to 100 times higher than what we get just using CO. The only challenge with this particular combination is that N2H+ is also very sensitive to the cosmic ray ionization rate, and this is a poorly constrained parameter in disk studies. So the project I'm currently working on, I'm trying to figure out if there are other molecular combinations that we can use to reliably trace the gas mass, and specifically figuring out what molecules do we need to use, what specific transition, and what functional form is useful. Is it a ratio of line fluxes or is it a more complex function? And I'm carrying out this work as part of the Disk Exoplanet Connection, or DECO Large Armor program, which is observing 80 protoplanetary disks with a spectra setup covering many different molecules, allowing us to explore this combination of molecules to constrain the disk gas mass. So specifically, just a broad overview of the approach I'm currently taking. So I'm building a large grid of this chemical model since we are constraining the gas mass, which is a global parameter. And I'm varying different parameters to capture the diversity of the DECO sample, but also building a grid that will be useful for the community. And also with this grid, we are then calculating the line fluxes of the different molecules that we have with the DECO survey. And then we are searching for trends between line fluxes and molecular line fluxes and disk mass using machine learning techniques. And then the hope will be to apply our findings to the DECO sample. So far in terms of progress, we've been mostly working on modifying our modeling workflow since we need multiple codes to model one disk model, so making sure it's efficient, but also we've been also choosing grid values to make sure it's representative enough and that will be useful for the community. And also as part of this work, we are conducting a disk chemical code comparison where we are comparing the results of 6 different disk modeling codes that we are using in the community in order to derive uncertainty on line fluxes. And then those uncertainties will be propagated in our large grid in order to have reliable disk masses. So stay tuned for more updates on DECO disk masses. So we're working on this multimolecular approach. I'm just gonna leave my key takeaways on the side, and I'm ready to take questions. Thank you.
Question for Amina? On the web? No. Okay. We can move on.
Okay, thank you very much. You can catch Amina later on. Maybe, thank you. We're moving to the next talk by Eva Gevorgen, who will be talking to us about the equivalence between simple, multi-layered and homogeneous laboratory-based rheological models in planetary science. Yes.
Hello, so I'm Eva. Thank you for the opportunity to talk.
We can't hear you.
It's better?
Yes,
Okay.
that's better.
So thank you for the opportunity to talk to you. So I'm going from disks and etc. just to planets. Okay, sorry, transit. This one. Okay, sorry. As data suggests for closing satellites and planets, most of them have a layered structure. As for example, in Enceladus, it has a subsurface ocean and icy crust on top of it and a core. So we have this kind of data for the planets in our solar system, but as farther we go from when we go out of our system, we don't have as much data to be able to model these planets with so much precision. And really, so where arises the question, when should we use real structure, real layered structure, and when we should use some models that are homogeneous and have less parameters to fit. Usually homogeneous bodies are easier to model, and they have less parameters to fit, easier to integrate. And if we are looking at some problems that the stratification is not really very important, we could substitute them with homogeneous bodies. So we try to answer here a question: when, under which circumstances we can go from a multi-layered model to a homogeneous body. And we could show that if we are interested in tidal dissipation of these bodies, we can easily substitute a multi-layered model where layers are simple, have simple rheology, by a homogeneous model with more complex rheology and less parameters to fit from the data. Why tides are important? Okay, so all interactions between bodies are never elastic between planetary science. So we always have dissipation, and effect of dissipation is very important for a long-term evolution of celestial bodies, stars, and planets, moons. The dissipation can be directly measured for some bodies, at least some parameters from which we can infer on the internal structure of this body. So this is an important measurable quantity. And as I said, they play an important role for a long-term evolution of systems. Dissipation in the bodies we can see here. So this is the formula for the tidal energy dissipation in moons and Earth-like planets. So here you can see that all the terms are this is just constants, and the important part is the K2 imaginary part of Love number, which can be measured for the planets. And so we want to see under which circumstances this K2 can be of a homogeneous body or of a multi-layered body. So we showed that the Love number of a multi-layered body can be very well approximated by the Love number of a homogeneous body with a more complex structure. So to do this, we usually use oscillators to represent the rheology of our planets. Rheologists have this kind of, it can be like generalized Voigt models, generalized Maxwell models. And so we have, these are viscosities and elasticities of models. These are just viscoelastic representations of bodies. So the tidal Love number of a multi-layered body can be expanded in this way, where we have expansion in various frequencies, and the same thing can be done for a homogeneous body. And so we find a connection between we can separate it into the elastic part and the non-elastic part, and find a direct correlation between the parameters of layers and the parameters of our homogeneous model. The advantage of having the homogeneous model that we can work just with certain modes, the dominant modes, and don't need to carry with us all the complexity of K2. And depending on the range where we are located, we can just use some of, for instance, we can just keep few of elements here, like like we can end up just with few parameters, so we can end up with a model with 6 parameters, etc., which is far less than the number of parameters if we have the real structure with all layers. So here I'm going to show you an example of application of this modeling to our moon. So we use the accepted structure for the moon, which is 5-layered structure, where we have a crust, mantle, the liquid core, solid core, and a molten layer, low viscosity molten layer. So you can see here the sizes of the layers and their parameters. So here we could show that for the moon it's enough to use a simple oscillator just with 6 parameters, in contrast to a 5-layered model. So as you can see here, this is a comparison between the, here you can see the comparison between the 5-layered model, which are the red dots, and our model with just a homogeneous model with 6 parameters that perfectly fits the imaginary part of K2, dependence on frequency. So we also have a real part of K2 for which we have measurements for the moon. And so you can see here, this is the measured value, and red dots is the 5-layered structure, and the blue one is the homogeneous structure. The same for quality factors. So the 2 measurements that we have for the moon, they fit pretty well on our model and also in a 5-layered model. So next question would be, how can we establish a connection between like the real parameters that can be measured for the moon or other planets and the parameters that we have in our modeling? So this is still in progress, but for instance, for the moon, we can see that the low viscosity layer is directly connected with one of the elements that I have. So we change, like, you can see that the dotted line is the 5-layered model, and the other one is our model. So you can see that the change is coherent. So we have a direct connection between the viscosity of low viscosity layer and one of the oscillators in our model. So another application, so if models are slightly more complex, and like if we have I don't know, if you look here, we have an exoplanet. We are modeling an exoplanet that has a more complex imaginary K2 with 2 peaks, which is not usual. So we still can model this with having a bit more complex homogeneous model. So like here, we add an extra element, still have 6 parameters to fit, but we can fit. So this is done with our model, and like previous figure is. So here, this is modeled with 5 layers, 5-layered structure, and here we have the same curve done with just a simple oscillator. And so here some conclusions. So the important thing is that we can indeed, if we are interested in just dissipation of a planet, we can use these simplified models and not carry all the complexity of layered structure. We can, for some planets, we don't even have enough measurements to be able to really say if structure, the layered structure is that one or is something else. So for the moon, for instance, the measurements that we have at this point, the 2nd-degree tidal love number and quality factor, are not enough to advocate for a presence of molten layer, for example, because even with our more simple model, we can fit the measurements. And so, and also if we are looking into a long-term evolution of celestial bodies, we really don't need to carry the complexity of multi-layered structure, and just can go to simple models. So some examples, and thank you.
Thank you, Yeva. Thank you very much for this presentation. Is there a quick question for Yeva? No? Okay, thank you very much again. And at this point, is Swastik Chobe in the room, or I don't see him remotely? So if not, we have the possibility to hear very quickly from Amir Vandal, who was going to present something yesterday, but he wasn't available. So he is going to give us a quick talk about subglacial habitability for the solar system, from the solar system to exoplanets.
Okay, thank you very much. Yeah, what do I check? Or do I change slides?
Green button.
The green button. Okay, so as you can see, observing exoplanets and biosignature outside the convex. Oh, no, that's the wrong one. That's the wrong one.
Well-
This is tomorrow.
Okay, well,
If they have the right one, this is the one.
okay.
Subglacial habitability from the solar system to exoplanets. And as you can see, subglacial, it's already on the picture. And I'll concentrate on red dwarfs, which is the other thing that you see in the title slide. Does not work. The green one. Yeah, okay. So at the first, I'll just advertise my new books that is here in the Springer stand in the conference, Life in Space, which is a result of 25-year coursework in astrobiology and astrophysics. And we are talking about the habitable zone in our solar system. It's well known approximately between the orbits of Venus and Mars, a little more. But if you are talking about the other solar system, we know that it depends also on the type of the star, which for our solar system, it's a green annulus. On other hotter star, it will be more expanded on cooler star, which are the most important for biosignature detection and also exoplanet detections. Red dwarfs are much smaller. So we can see it in the following diagram, where on the vertical axis, we have the stellar surface temperature, and on the horizontal one, which, yeah, you see it better, it's a distance from the star, of the planet from the star, and you actually see the solar system, which is just beyond 6,000 degrees K on the vertical axis. Earth is just in the middle, approximately in the middle of the habitable zone, which is in the green. And cooler star, the habitable zone will be much closer. So this research, this work, our work in the last few years, and in particular in the last 2 years, the habitable zone is in yellow. It's a diagonal stripe. And the horizontal axis is a distance in AU from the host star. And the mass is also another proxy of the surface temperature, depends. So our sun is, of course, G-type star is 1 on the vertical axis, and we have the solar system there. But what we see that there are regions outside of the yellow stripe, which this researcher extends the habitable zone, either for hot locked planets in close to their host stars, or for cold planets out under ice cover outside the conservative habitable zone, the traditional habitable zone. And what we see in our solar system, we know that there is water, plenty of water exists under the ice covers of Enceladus and Europa, and even recent observations of the plumes of the geysers have found some biological molecules. But if you look at red dwarfs, they have several advantages. Even if you look about the surface, they have a very large range of temperatures on their surface because they are locked. They have cold, in the night side, they have cold region, in the day side, they have hot region, and they have many advantages of detecting biosignature. First, because the planet is closer to its star, so it's a shorter period, more transits, bigger planet to size ratio, which gives you a better signal for detecting either dimming for exoplanet detection or biosignatures in the transmission spectra. And here we see as just a simple diagram. What would, if Earth would be locked, how would the temperature distribution look like on Earth? And here we have the real temperature distribution on a locked star. So we see that between the hot substellar point and the cold night side, there is a large temperature difference, which enables a much more extended habitable zone. But even more than this, in a recent paper in Nature Communications, I've shown that the habitability can be extended even more if you consider subglacial liquid water on planets of M-dwarf stars and also on other stars if you look for colder regions. So you have here the highlighted thing. I have no time to, but you can read it yourself. And here we have again the habitable zone as a function of a stellar mass on the vertical and the distance from the star on the horizontal axis, and the solar system is up there near the G-type star like our sun. And this is another presentation of the habitable zone and the boundaries of the optimistic versus the conservative habitable zone. Well, we have it here in the same temperature scale on the vertical axis, but the horizontal axis has, rather than distance from its host star, it has a flux on the planet. And here we have another presentation of the same one. This is taken from the Nature paper. And we see how much this can be extended if you consider, on the one hand, on the left side, we have the hotter planets, which are closer to the stars. And we can compare it to the well-known, we have in blue, dashed blue are the new limits of the habitable zone. This is because ice can be formed on the night side of the locked planet. And under this ice, you can find liquid water. And on the other hand, on the colder stars outside, on the other side of the habitable zone, you can take an example from the Martian polar lakes that are subglacial, and if they can be formed on Mars until a certain solar illumination, then you can take this as a limit. So these are the two limits of this new research, and you can see this diagram in a little different. This is taken from the recent astronomical journal paper. So this time the horizontal axis is inverse. So the higher the flux is on the right side, and you see the traditional habitable zone in a green stripe. And you see the yellow stripe is a low tidal lock boundary. Under this yellow stripe, you have locked planets, and you see a lot of new found planets, some of them famous, like the TRAPPIST-1 system, are in the locked region and outside the traditional habitable zone. Yet they can have liquid water under the ice according to this model. And actually, this is not just a model. It has been already found in several of them. See if I can show them. I'll show them in a minute in my previous, almost last slide. But before this, I should say a few words about transmission spectroscopy. This is a method by which we hope to find life soon, evidence for life, like ozone or some combination of oxygen and methane and CO and so on. And some molecules have been already found by this. So if you don't know what transmission spectroscopy is, it's this illustration just on the upper left shows you. I have no time to explain it, but you probably know. So here we have the transmission spectrum of TOI 270D, which have recently been shown to contain some significant molecules, which can even like methane and CO2 and carbon sulfide and others, which could have even hint is the existence of a of an ocean. So it's Haitian Ocean. How much? How much do I have? 2 minutes. I'll try. Yeah. So if this exists there, if water exists there, and also on a second planet, then they should be explained. Same thing about other planets like GJ 486b, which have been shown signs of water. So could water and biosignatures be detected on hot, locked, rocky planets? Stellar flux on this planet is much higher than on Earth, and the calculated average surface temperature is hundreds of centigrade. So how could water exist? How can we see it? And also the atmosphere and water would be eroded by the XUV wind and stellar wind from the red dwarf host. But actually water could survive, according to the model I described before, under the ice on the night side of those planets. And we have actually an experimental proof that there is some water there. There are some comments below, but never mind. So here we have circled the best candidates for water that theoretically could not exist unless you accept some model like the one that I presented. So I said already GJ 486b and TOI 270b and probably also D, and the TRAPPIST one, C and B. And well, I'll skip this and I'll just switch to my conclusion.
Yes, you can probably just leave them up there because we don't have very much
We'll
time.
stop there.
And I suggest that you catch Amory perhaps during the lunchtime or the coffee break. Thank you very much. We need to move on to the next paper, which is by Amina Bulkabul, and that is going to be an online presentation. Is Amina prepared to go to his presentation?
Yes, can I share my screen?
We don't see your presentation.
But you can start speaking. We can hear you.
Okay. Can you see my presentation now?
It will be on in a minute. You can start speaking.
Okay, thank you.
You have to put your presentation, did you?
I did put it. Can you see it now?
No. You can't see your presentation yet, Amina.
Do you have the presentation? Okay, please.
Yes, please display it from here. Yeah, you can start, Amina, please. Amina, can you hear us? No. No. We lost Amina Bulkabul. Can you hear us? No. Okay. She's reconnected. I need to connect it. Amina, can you hear us? Okay, I think we lost the connection with Amina. All right, so while we wait for her perhaps to reconnect, we are going to go to the next talk, which is an invited talk by Raphael Luc, the demographics of small transiting exoplanets. This is an invited talk. Can you please put Raphael's presentation on? Hello? Yes, please.
Thank you very much. My name is Rafael Luque. I'm a Sagan Fellow at the University of Chicago, and next year I'll be back in Spain as assistant professor. I'm going to give an overview of the field of small exoplanets. There has been some topics that have been covered already, but yeah, I'd like to thank the organizers, Antonella, and the rest of the division for inviting me to be here. So, and for the sake of time, I'm going to skip this beautiful video in which shows the exoplanet discoveries as a function of year. They are color-coded by technique, but you can see it in the booth from NASA. They have this video, and they have it updated up to, I think, more than 5,000 planets, so you can continue seeing it. So, but the main point to come here is that most of the exoplanet discoveries that we have done today do not resemble our own solar system. This is a diagram in which we show the mass of the mass in terms of units of the Earth, and the period, the orbital period of the planets here is the solar system. And most of the information we know today, it is not representative of what the solar system is. We see two blobs, mostly from transit technique, which are the blue ones, that they are limited to short periods. These are due to detection biases. And we have orange points more or less distributed into this diagonal line, which is also related to detection biases. We have three blobs, mostly hot Jupiters, these small exoplanets that are between sizes of Earth and Neptune. And then we have these Jupiters that are more analog to our own one. So what do we do with this population? How do we make sense for it? From the previous talk, we heard that understanding planet formation from first principles is really, really tough, right? We need to go from micron-sized grains to full planets. So this is a change of 12 to 14 orders in magnitude in size. We need a 40 increase orders of magnitude in mass. So what we typically do, instead of going from first principles, we try to take a demographic approach. So the main function here that we try to determine is the frequency and the distribution of planets as a function of another parameter. And we hope with those parameters to learn something about how this population form and evolve. The typical parameters that we are interested in are the host star properties such as mass, the stellar metallicity, but also distance and other properties. So this is the hypothesis. What we do is that the planet distribution, the final planet distribution that we detect, may have the physics that are from planet formation and evolution. But there are many parameters. There is large-scale migration that may erase a lot of information from initial conditions. And also there are different methods that are proving different parts of the parameter space. So they are constraining different parts, and we cannot certainly take all the information just at once to trace all the possibilities of planet formation. So what were the first steps in demographic studies were driven by the radial velocity surveys. And this is the main takeaways that we can take from these studies that were starting in the early 2000s. We know now that for solar type hosts, small planets are at least an order of magnitude more common than giant planets. This is from this plot. We also know that the frequency of giant planets increases with increasing period. So this kind of thing, and there seems to be a turnaround here. So there is kind of a maximum efficiency of giant planet formation. And this peak seems to be close to the ice line of the system. And there is also an occurrence rate of giant planets in short orbits that increases with host stellar mass and metallicity, meaning that apparently the more material there is in the disk, the easier it is to make giant planets. And this is coming from this plot. Those are kind of information that we know today that it is true. There are some caveats, there are some complications, but this is kind of the main takeaways we can take from here. But this is mostly for giant planets. So Kepler was the first mission that really gave us some insight into the properties of small planets. Kepler uses the transit technique, and to understand the revolution that it implied, there were only 50 known transiting planets prior to its launch, and after the primary mission, there were 2,500. So these were the Keplers that were the transiting planets that were falling within the field of view of Kepler, and this is what happened after. And you see that most of the points here are kind of orange and green and some blue. So they are really small planets compared to what was the population known till then. What we know from transit demographics, what are the main results from Kepler mission, is that compact multiplanetary system normally tend to have regular spacing, meaning the planets are kind of regularly spaced, and they have similar sizes. This is also known as peas in a pod type of pattern. We also know there is a hot Neptune desert, meaning that there are no Neptune-sized planets that are very close to their stars. We know that there are rocky planets very close to their stars. We know Jupiter planets that are very close to their stars, but there seems to be an absence from Neptune-sized planets. And we also know that for a short period, small planets, they seem to be much more common when they orbit metal-rich stars, the same that we saw for the giant planets. The more material, the more metals there is in the disk, for a given star, it seems to be easier to form planets, small ones and big ones. This is probably the most interesting or the most surprising result that Kepler provided in its lifetime. This is called the radius gap. And here, this is an important changing axis. We are going from number of measurements or number of planets that we have detected to actually a quantity that tells us what it is happening. This is truly an intrinsic occurrence rate, meaning how many planets are per star statistically in the Milky Way for some given conditions. This has been corrected for all the detection biases that I told you before. And as you can see here, even though we have detected hundreds and hundreds, even thousands of hot Jupiters and Jupiter planets, they seem to be very rare. But these type of planets are very common, and they are the ones that do not exist in the solar system. So these are Earth for reference and Neptune and Uranus for reference. And we have here a bimodality that has been known as the radius gap that separates two populations that we have classified as super Earths and sub-Neptunes, but that we know almost nothing of. They are the most common type of planet at short periods in the galaxy, yet they do not exist in the solar system. And this is what is the topic of my research, is to learn what this population is made of. There are two options. One option is that these planets, super Earths and sub-Neptunes, they are the same class of planets. They are some planets that have atmospheres and do not have atmospheres. And the reason or their connection is that they have lost them. Planets are born like sub-Neptunes, I end up as super Earths, depending on the conditions. But there is another theory, or there is another option, which is that these planets are two different populations. One that is super Earths, planets that are slightly larger than Earth, and others, these sub-Neptunes, that could be water worlds. These water worlds would be more like a comet, a very big comet, that ends up going into the inner parts of the system, and it would contain a large water mass fraction, something that has formed beyond the ice line of the system and has migrated in where we detect it. The internal composition is heavily discussed, but this seems to be a common output of planet formation models. So the problem is that both observations, the observation that we have of the radius gap, are very well explained by both theories. We can have planets that are sub-Neptunes going into super Earths due to atmospheric evolution, just simply radiation that can evaporate or not evaporate the atmospheres of sub-Neptunes and become them super Earths, or retain them under certain conditions. But we also have from planet formation models, we know that formation beyond the ice line is very efficient, and migration is something that is very common also in planet formation models. So forming a large planet that would be beyond the ice line with a lot of water and migrating it in, it's something that planet formation models tend to predict. However, we have here this dichotomy that it is all holding onto one measurement, which is planet size. And here we see two balls of the same size, but they have clearly different compositions. So density, really, it's an important parameter that we start to add in the last years into these studies, because Kepler is only providing us size. So for ENDORS, this was possible before, because we had instruments in both the transit technique and the radial velocity technique that can measure radius and masses very precisely for small planets. This is just a detection bias thing. That is why it is easier to do it for ENDORS, because of the lower mass, lower size of the host star that allow us to go all the way to Earth-like planets up to the Neptune size with high precision. And these are some of the instruments that have been studied, that has been used in the last years to increase the population of transiting planets with measurements of both the radius and the mass. So this is a population plot. In here, we plot the radius and the mass of all the known transiting planets orbiting ENDORS a few years ago. And here we have precise measurements, real measurements for all these populations. So we can start doing demographics, not only in radius space, but in mass and radius space, in density. And here we can see that we have kind of two populations. We have one population of planets that they align to this line. This is not a fit. This is just an Earth-like composition, how it looks like in a mass radius diagram. And here we have something that is less dense than the Earth-like composition, something that could be composed about half water and half rock. Doesn't necessarily need to explain that these planets have exactly this composition, but they have overall a density that is consistent with being much smaller than what the rocky planets are. And then we have a small population here that necessarily needs to have hydrogen atmospheres in order to explain their big size and small masses. So we can divide this sample into three populations according to their density. We have rocky planets that are here. This is just kind of a normalization in density is the axis, and the density is normalized to Earth. So we would have like kind of these rocky planets, these water-rich planets or low-density planets, and then we'll have some puffy subneptunes that truly have hydrogen atmospheres to explain their low densities. And we can see that while in radius, the gap, it is still here. You have the shape here of the radius gap that we saw before. The populations are mixed in radius, while if you do it in density, there is a clear spacing between what the rocky planets are and what these volatile rich planets are. They are separated in density, but not necessarily radius is a good proxy for that. So if we compare this population, observational population with models, the data agrees very well with the predictions from planet formation. Here, there are different flavors. This is planetesimal accretion. This is pebble accretion, but they are still be able to reproduce very well the observations. However, this was the case by the time we presented this, and this was kind of in favor for the water-rich or the water worlds hypothesis, but developments in the gas dwarf in gas dwarf models, meaning Earth rocky like Earth-like cores, rocky with just simply hydrogen on top. New models have been able to reproduce this kind of tight relationship in planet mass and size. So right now it is clear that mass and radius measurements alone are not sufficient to distinguish between if subneptunes are water worlds or if they are gas dwarfs, something more like a rocky core with hydrogen. So what is the hope? The hope is atmospheric characterization. There seems to be some promise about if we can distinguish between these two scenarios. This would be more like a gas dwarf, a massive hydrogen atmosphere on top of a rocky core, or something more like a water-rich interior with a smaller atmosphere on top. There should be some features that are different for these models that we could distinguish with JWST. And the first results have been so promising just to demonstrate the capabilities of James Webb to tackle this question, but they has brought more questions than answers so far, I would say. So the few observations that we have done for subneptunes today have been mostly, the most relevant have been for GJ1214b, K218b, and TOI270d. We saw before the spectra of TOI270d, but the atmospheric results are challenging to connect to the interior properties of the planet. Here, for K218b, we have a lot of detections, several bumps of methane. We have also CO2. This has been detected for K218b, but we also have water in TOI270d. We also have sulfur dioxide in GJ3470b. So right now, it is difficult to connect the interior properties of the planet with the observations we have done so far with JWST. But JWST has demonstrated to have the capability to do these measurements. So it is certainly that in the next years, this will get more answers. So what's next? We want to do demographics of small planets. We have the possibilities of doing transit and radial velocity, and now atmospheric characterization for this population. But what else is missing? What can we do next? For the younger population of this audience, I would say Plato, JWST, obviously, because it's going to have a long lifetime, but also Ariel are gonna be key ingredients that can be added to this. And Ariel, most importantly, is going to be able to do demographics of exoplanet atmospheres. This will be a first. JWST is going to do a lot of small detailed characterization of a few candidates, but Ariel, it is its mission to do a demographic approach. So it will observe hundreds of exoplanet atmospheres. And Plato is going to provide a lot of precise stellar characterization for all these hosts. So we are going to have very rich information of the stars that are orbiting these planets in order to trace from the first slide demographic as a function of stellar properties. Plato is going to give us that. It's going to give us very precise stellar properties. Plus, it's going to increase the detections that Kepler was able to do. So what about the long period small planets? I've been focusing on this population here, but what about these ones that are more like ours in the solar system? So here we are gonna need to rely on complementary detection techniques. So astrometry, Gaia is gonna fill this kind of triangle here in the next years. The direct imaging missions, it will be able to collect, to fill this part. But microlensing with Roman and also the Habitable Worlds Observatory are going to fill this part of the parameter space that will be more similar to what Earth 2.0 has been claimed. So I'll encourage you to see the talk tomorrow by Professor Mark Clamping, the director of NASA Astrophysics, on the Habitable Worlds Observatory and how this is a project that the young people should go aboard as soon as possible now, when it is early. So I think coming soon in terms of demographics, we'll be able to have some kind of family portraits because direct imaging is going to enable to see the whole system at once. We'll be able to have a spectra for all the planets at the same time. And I think another avenue that we need to do in the future is to connect these different detection techniques in order to have joint inferences in the demographics. So here it's one of the first attempts at doing so, in which they are combining radial velocity, transit observations from Kepler with microlensing results. So trying to do these joint demographic inferences with different techniques, combining radial velocity, microlensing, transit, direct imaging in the future is going to be also very important. So I'm going to leave you here, if I can, with my summary, and I'll be happy to take any questions. Thank you.
Thank you very much. Thank you very much. Excellent review of the current situation. Are there any questions for Rafael? You need to go to the microphone, please. Yes, in the back. And while you're doing that, thank you. And indeed, we have been arguing also for some of the moons in the solar system that are ocean worlds and big satellites, that they, as ocean worlds, do represent a category of exoplanets, an intermediate category that is very much populated. And Ariel, with more than 1,000 targets, should be able to characterize these moons.
Yes, very exciting times.
Yes.
Yeah. No, thank you for this great talk. So it's actually, how would this gap in the radius look like if you showed it in mass? And could your explanation show the difference between the radius and mass presentation of the sub-Neptune desert?
Yeah, this is a great question. So the radius, the good thing is that we have had thousands of planets that we can put in radius space, and we can see these features very, very quietly. We don't have masses for that many of these planets. So for the smaller population that we could do so, the Endwars, the clear division is in density, not necessarily in mass, because in mass we saw from before, here we can see that this kind of part, it's all full. So you go from 0.1 Earth masses to 10 Earth masses, kind of fill the whole space. So it is difficult to see something here in mass as a gap, but it is possible that this is just a low number statistics. So it is possible that there is a dearth of planets of about 3 to 6 times Earth masses. So we have many small planets, and then we have one of the more massive ones, and these ones, some of them can have atmospheres or not atmospheres. But it is possible that there is also a mass gap. Clearly in density, it is seen more easily because it goes along these lines. We don't have a gap in this direction. We have a gap in this diagonal direction.
Okay, a very quick last question, please. No.
The question is about Gaia planets. Where are they expected to come out, and will they add to this distinction between the Neptune's models?
Yeah, I'm not a Gaia expert, but I believe that DR5 is going to be the first data release that will allow to see to have a time series. DR4, sorry,
Yeah.
DR4 will be the first data release that will have time series of these proper motions that you could trace back to exoplanets. So I think DR4 it is planned for 2028. I'm not sure if it is that late or a little bit earlier, but it will all become public at once, right? So there will be a realm of information available, and they are expected to have thousands of exoplanets filling this part of the parameter space. So there will be a lot of information to extract from there. How good do we go to the Neptune regime will depend on the amount of detections and the actual precision, because we have never explored this in astrometry. We have only done a few detections in astrometry, and they have been kind of this type of planets, very massive and short periods. But we don't know yet this because we have never got this data set.
Okay, thank you.
Okay, thank you very much again. And we are going now to try again with Amina Bobako. I don't know if you want to try and share, Amina. Otherwise, we're going to show your presentation here.
I apologize for the earlier technical issue. I'll try to share my slides now. Can you see them?
I think it's coming. Yeah, we can. Go ahead, please.
Oh, thank you. I am Amina Bobako, a researcher at Algiers Observatory. I'm going to talk about a new candidate planetary companion to the radial velocity standard star HIP 10,000. Presentation. Companions is the radial velocity method in spectroscopy. However, detecting planetary companions when the radial velocity signal have very low amplitudes is usually faced or challenged with several problems. In fact, the radial velocity variation can also stem from both intrinsic stellar phenomena such as spots and oscillations, but also from instrumental factors. So in this presentation, I'll focus on the star HIP 10301, which is used in the calibration of the wavelength of the radial velocity spectrometer on board of the Gaia satellite. This star is known to harbor two planetary companions. So we aim to validate these planetary systems and try to discover new ones while taking into account the possible contamination by parasite signals. So to search for planetary companions, at first, we need to measure the radial velocity. We do this by matching maps observed spectra with theoretical templates from Marks-Amber plane parallel and spherical atmosphere models, which are available in POLIX database and suitable to poor stars. I should note that HARPS pipeline provides both 1D and 2D spectra. 2D spectra are in the wavelength ordered space, while 1D spectra are the final spectral product, which are merged, reband, place corrected, and corrected to the barycenter. So the matching process relies on minimizing the quadratic sum of the difference between observed and synthetic spectra, which is the chi-square. In the 2D case, we make sure to avoid strong telluric lines and Ca2 H and K emission lines. So we set the wavelength edges to the spectral range from 3,990 to 6,200 angstrom. The intersection of these 72 Hertz orders with the wavelength edges yields 52 orders to be treated. In the 1D case, we select these 5 spectral ranges. So we adopted a simultaneous fitting strategy of these orders. So we minimize the total reduced chi-square of all orders and all spectra over the total degree of freedom. So this permits the selection of the best templates matching the target. Preliminary estimations of the radial velocity and rotation velocity are deduced from least square fit in Fourier space, while their optimization is achieved by Levenberg-Marquardt algorithm. The minimization process permits the selection of the best template with the atmosphere parameters, which are the effective temperature, surface gravity, metallicity, and alpha process element ratio. I list here the atmospheric parameters of our target, where V broad is the rotation velocity of the target. After measuring the radial velocities, we can search for periodic signals. We do this by applying the generalized least square periodogram to the RV dataset. But at first, we need to construct the empirical cumulative distribution function in order to get the significance level. After constructing the ECDF, we apply the GLS to the RV datasets and frequencies in the periodogram which exceed 95% of the significance level are considered as significant. And these periods or frequencies are then implemented into Zekmester and Keplerian algorithm to determine the rest of the orbital parameters, which are the RV semi-amplitude, eccentricity, longitude of periastron, and time of passage through periastron. I show in this figure the ECDF of our target's radial velocity 2D dataset. Now I discuss the 1D spectral results. Applying the GLS to the 1D radial velocity dataset, I obtained these two periodograms for which the highest peaks correspond to the two known planetary companions of 14 and 53 days. The red horizontal line is the significance level determined from the ECDF. So subtracting the orbital solutions of these two periods, we obtained a long period of about 3,000 days. We assume this period is related to the magnetic cycle, but how can we confirm this? In fact, we can search for periodic signals in one of the magnetic activity indicators, which is the S index, which is given by this relation where H and K are the total fluxes in the CA2 H and K emission lines, R and V are the continuum fluxes, and alpha is a scaling factor. So applying the GLS to the S index data set, we obtained a long period of about 3,000 days, which is close to the one detected in the radial velocity data set, which proves that what we detected there is indeed related to the magnetic cycle. Subtracting the long period, we detected a short period of about 19 days. This period could have two possible sources, either new planetary companion or stellar rotation. Stellar spots rotate with the star's rotation period, and since they are regions with lower temperatures compared to the surroundings, they create a deformation in the spectral lines, which induce a radial velocity variation with the star's rotation period. So now we need to estimate the rotation period of the star. Here, we can also use the S-index dataset. So we applied the GLS to the residuals of the S-index and obtained a short period of 38 days, which could be the rotation period of the star. We see that this period is close to double of the radial velocity period of 19 days. So what we detected in the radial velocity could be a harmonic of the star's rotation instead of being related to a third companion. But what do the 2D spectral results reveal? As I've said before, the 2D spectra aren't corrected to the barycenter. So here we process with two different approaches. At first, we don't correct the wavelengths to the barycenter, but instead shift the final measured radial velocities with the barycentric Earth radial velocity. Applying the GLS, we obtained the two known planetary periods in addition to the magnetic periods. But surprisingly, in the residuals, we detected a peak at 1 year and its first harmonic. And there was no indication of the 19 days period in the residuals. However, in the second method, we corrected the wavelength to the barycenter before measuring the radial velocities. And here we were able to recover the 19 days period, and the peak at 1 year was considerably reduced. So from these two results, we deduce that when dealing with 2D spectra, it's better to correct the wavelengths to the barycenter before measuring the radial velocities. So here we've detected a short period of 19 days in both 2D and 1D spectra, but this period is close to half of the rotation period. How can we prove that it is related to spots or not? We know that spots have low contrast at longer wavelengths. So any signal related to spots should have a variable radial velocity semi-amplitude. So here we need to measure or to search for periodic signals at two different spectral ranges, let's say blue and red regions. If we do this, we have to find different radial velocity semi-amplitudes if we assume that the signal is related to spots. So from this, we obtained in the blue spectral region another period of about 17.99 days, which is a combination of the 19 days period of the red spectral region and the 1 year period. We also noted that their RV semi-amplitudes are about the same within uncertainties. And the peak at 1 year is higher in the red spectral region. So here we can say that the red spectral region is influenced by a 1 year signal, which we can't be discussed right now because of limited time. So if the signal in this region is influenced by a 1 year signal, then we deduce that if any planet could exist, it should have a period of about 17.99 days. We also estimated the correlation between the chromatic index and the radial velocity, and we found no correlation between these two variables, proving the independence of the signal from the spots. So here, for this target, we detected third planetary companion, and there is a high possibility that it has a period of about 17.99 days. So in conclusion, in this study, we proved that when dealing with 2D spectra, it's better to correct the wavelength to the barycenter before measuring the radial velocities. And for our target, HRB 10,301, we detected a new short period of about 19 days in both 1D and 2D spectra, but it is close to the half of the rotation period. And when searching for periodic signals at different 2 spectral ranges, we found the independence of this signal from the spots, which proved that it is not related to the rotation period. And it suggests the existence of a third planet to this target, and there is a high possibility that it has a period of about 17.99 days. And thank you for listening, and welcome for any questions.
Thank you, Amina. Thank you very much. We don't really have time for questions, but people can interact with you. And I'd like to
thank you
everybody in this session and all our speakers, and we reconvene at 1:30. Thank you.
Hello. Yeah. Can you take your places? Hey, well, good afternoon. I'm Gonzalo Tancredi. I'm the chair of this session in collaboration with Sonia Farnacier. She will also be doing the chairship of this session. So we will start with a remote presentation by Bren Arkinal, a report from the Division A and F Working Group on Cartographic Coordinates and Rotational Elements. He has 10 minutes.
Yeah, okay. Sound check. Can you hear me okay?
Yes.
Okay, thanks. Okay, thanks for the introduction. So today I'd like to present information on the IAU Working Group on Cartographic Coordinates and Rotational Elements, which is a Division A and F working group. And I'll acknowledge the rest of the members of the working group as co-authors here, and they'll be listed in a later slide. So, so I advance to the next slide. There we go. Just an overall view of what I'll be speaking about, an introduction to the working group and our recent activities, changes for our next main report that we plan, and information on improving the lunar reference frame, and also on the future evolution of the working group. And of course, we certainly welcome input and discussion now or afterwards. So a little bit of background on the working group, that the main purpose of this group is to promote the use of a standardized set of mapping parameters for solar system bodies. We make recommendations. They're always open to further modification, but they're intended for the use and comparison of multiple data sets. We issue reports with these recommendations and related parameters with the goal of making cartographic products, maps of solar system bodies. The working group was created in 1976 and has been an IAU functional working group since 2016. Starting in 1979, the working group has issued these reports and recommendations about every 3 to 6 years. The current report was published in 2018 with an image at the center there, and these reports are available from our website as shown in the image on the right. So the working group operation is by membership by invitation or volunteers, and you can see the list of our 15 members on the right, people from 5 different countries with anywhere from 6 to 48 years of membership. One of our original members is still active. We consider new published coordinate system determinations and published papers. We recommend standards based on consensus from our group and input from others. We don't have any independent resources funding of our own to do this. We don't bless or enforce these recommendations. We're simply providing them as valid and consistent recommendations that are a reflection of general consensus and use. These recommendations are primarily for mapping, but are used for other things, dynamical determinations of navigation, and we don't tend to deal with formats and lower level types of mapping standards. So as to recent activities, for a few years, we spent a great deal of effort making presentations and publications and meetings about the future of the working group, asking for input to the working group of what we were doing and how the working group should continue. I'll talk about a little bit about that more below. We're not particularly successful getting a lot of input, partially due to the nature of virtual meetings for a few years, but we may try to do a community survey and collect more information. For about the last 2 years, we've been providing a lot of information on the lunar reference frame with the anticipation of making an update to it. I'll talk about that. We're also continuing to make, of course, our annual and triennial activities reports to the divisions. And you can look at the IAU web pages for those reports and lists of all the publications we've been doing. We're always seeking new members for the working group. We completed a new members packet that we can provide for people who are interested in joining, and certainly further volunteers are welcome. We'd like to get on to our next main report, but we've been delayed due, of course, like everybody else, due to the pandemic workload and efforts to make our previous presentations and collecting input. We have spent time working on lunar reference frame issues. So some details on the contents of our likely next report are here. Again, I'll talk in a moment about the lunar reference frame. We probably will make an update to the Mars reference frame and orientation, because there was accidentally a change of about 100 meters in longitude in the last reference frame. We'll also make updates from missions over the last 10 years throughout the solar system, and updates even from terrestrial observations with large telescopes doing mapping of nearby asteroids. We continue to insist on coordinate system and mapping issues with questions from various groups and helping with reviews of journal papers. But we're aiming to try to get this next report out soon, perhaps by early 2025. So one slide here on the cartographic lunar reference frame, and actually I'm doing a presentation in the concurrent session in A4 coming up on the hour, and you can listen to that for more details. But the summary here is that there are two systems in use for the moon, the mean Earth polar axis and principal axis systems. Current recommendations are to use, of course, the mean Earth system, since that's been used all along for cartography. The NASA Lunar Geodesy Cartography Working Group, with international input, recommended in 2008 the use of the JPL ME420 frame and ephemerides. And that was in turn recommended by the IAU Working Group in its 2011 and 2018 reports. And essentially all lunar data since that time by all nations, all space agencies, has been placed in that system. Basically many petabytes of data, billions of images, billions of LiDAR measurements. The issue is, should the frame be improved? And certainly several NASA working groups have recommended changes, and others as well. There's more data, there's better modeling and to determine the reference frame internally, and better ephemerides results. The critical function in all this is to maintain the coordinates of surface features. When you do an update, you don't want to see a change in coordinates of features on any planetary body. So we're not looking for a new ME frame from first principles, which may shift around somewhat, but a cartographic frame. And such a frame is available from the DE440 frame provided by Ryan Park and others from JPL. And it matches the DE421 ME frame, at least with the coordinates of the lunar laser ranging points at about the 9 centimeter RMS level. And some people have recently suggested that a principal axis frame be used instead of the ME for mapping and navigation. And we're frankly not clear entirely why. There'd be an up to 875 meter offset between the frames. Such a big difference is likely to cause substantial confusion and high costs for converting data and map products. So the goal and any advantage of that needs to be more clearly explained. So feedback is requested on either of these ideas, a minor update or a major update between systems. As to the working group itself, we've been in operation for 48 years now and have considered various issues and accumulated experience over those years. We have worked with many other groups that do these types of related efforts. You can see the huge list here on the right, and there are probably others. So what type of coordination is really needed between all these different groups? And you can see our 2020 white paper that was submitted to the NASA Decadal Survey that covers these types of issues, is what type of work could be done in the future and coordination and so on. Long term, what should be done with the working group? And for example, should the working group just continue in expanded form, more members, additional resources perhaps even funding provided for the members by space agencies that are where this work is important? The working group could be supplemented by other smaller working groups, the geodesy cartography working groups that have helped in the past. There could be some new structure like the International Earth Rotation Service and Reference System Service with a brief description of it there on the right, where there could be operational components for cartography and standards. There could be an oversight board. There could be dedicated staff helping with this. And the amount of work that the IRS does may certainly be greater, but it's not necessarily more complex. The IRS has one body to worry about, while the working group has 97 solar system bodies that we track, and there'll certainly be more, of course, in the future. So ending up here, I'll just say that we have our reports posted online, and you can take a look at them and see the references therein. The most recent report has details of the changes in it and available from our regular working group website. And there's a decadal survey report that we did as well. So if there's any questions, certainly contact me at the email address given here. I'll mention that I do have to go into the other session soon, so you can reach me there or in the later Division A session, or of course by email. I'll also throw in an advertisement here on the right of the IAU Symposium 401, Advancing Reference Systems, Ephemeris, and Standards, taking place in Argentina in a year. And of course, it is those topics looking at issues for the Earth and the Moon and the entire solar system. And there's a presentation in the next Division A5 session about that meeting. So that's all. Thanks for your attention.
Okay, thank you, Brent. Is there any questions from the audience? I have just a short question. Could you give me some more details about this meeting in Argentina next year? What would be the topics that would cover?
Yeah, sure. I can say only a little bit briefly, but again, Alberto Escapa is giving a talk at 1625. You can hear his presentation about the meeting itself. But the idea is to cover reference systems, reference frames, mostly, frankly, for the Earth, and also the sky, the celestial reference frame, but certainly covering planetary bodies. There's been a lot of interest, as you may have just figured out, from the Moon and also Mars and other bodies. So that's the overriding topic is reference systems, reference frames for the solar system. I hope that helps.
Okay, thank you. So if there is no other question, then we thank Brent again.
Okay, thank you.
Now we invite Ryan Park to present the report from Commission X2, Cross Division Commission, Solar System Ephemeris.
All right, great. Good afternoon. I'm Ryan Park, and I'll be giving a report on the, I'll be giving a report on the Commission X2 Solar System Ephemeris. Just to point out, this package was really made by Fabrizio, who unfortunately could not make it, so I'm really presenting on his behalf. So starting with the 2024 election and board handover, Fabrizio will be moving to the advisory role, and I'll be serving president of X2. And we also have the newly elected Vice President Dmitry Pavlov and two OC members, Daniel Hastrofer and Davide Farnokia. Just to give a quick background, when it comes down to the planetary and satellite ephemeris, the main contributors have been NASA JPL, IMCC, and the Russian colleagues. But now we also have contributions from our Chinese colleagues. Another thing to point out is that we expect to get a rapidly evolving and both in quantity and quality the data for these small bodies, thanks to the Vera Rubin telescope, FlyEye, and the NEO Surveyor. So starting with some of the activities from the JPL side, the E440/441 is still the latest available planetary and lunar ephemeris that's recommended from the JPL side. And every time we collect additional data for the inner planets and the moon, we do what is called a pass-through to see how good the data is. When the data starts to degrade, that's the time that we decide to do another general purpose ephemeris release. So what I'm showing here is just to give you an idea based on the Mars orbiter data, the ranging data based on the E440 that was released back in June of 2020. The prediction for the past 4-ish years fluctuates at the level of about 10 to 30 meters. So we will probably make another release in the next possibly 3 to 5 years. We also have continuously updated the ephemeris for the Jovian system. We have, thanks to the Juno radiometric data, we have updated the Galilean satellite ephemeris, as well as the Juno Jupiter System Barycenter, thanks to especially the Juno's flyby of the IAU Europa and Ganymede. JPL also released the JUPE 344 and 346 last year, which provides the updated orbit information of the irregular Jovian satellites. And on the Saturnian side, Bob Jacobson and company have reprocessed all of the Cassini radiometric data, including the ground-based observations, and released the SAT441, which includes the updated models for the Saturn's dynamics as well as the orientation model. Was published back in 2022. And based on the SAT441, updated gravity, topography, and rotation model for the Enceladus is also available. Also, the SAT-452, which provides the updated orbits of the irregular Saturnian satellites, is also released in 2022. On the Uranus and the Neptune system, the orbits of the irregular Uranian and Neptunian satellite have been released earlier this year, called the URA-117 and NEP-103. And lastly, the Pluto system was released earlier, I believe this year, called the PLU-063, work done by Marina Brozovic. And just to note, all of the products that we just talked about here are available on the SSD website, either through the Horizons Ephemeris Query tool, or you can also download the SPK file from the NAVE server. Moving to the contributions from our Russian colleagues, EPM 2021 was released a couple years ago. And the work is summarized by Petieva et al. 2022, which includes the additional lunar laser ranging data, additional ranging radiometric data from the Juno spacecraft, and also from the Mars orbiters, and also includes the improved modeling of the radiometric calibration, as well as the improved way of determining the asteroid masses. And also, they have published a paper a couple of years ago on the improved estimate of the solar gravitational parameter, or essentially solar GM. The work is summarized in the Oxim and Pavlov in 2022. Another contribution that they have made is they looked into the subtlety in the numerical issues involved when you're trying to do a planetary ephemeris integration, and this work was summarized in the Subroutine 2023. And last two bullet points are something that the Russian colleagues shared at the past Journey meeting. One of them is the lunar laser ranging data could be used to provide a constraint on the strong equivalence principle. And also there's a possibility of using the LRR data to improve the Earth's orientation parameters. Moving to the sort of a new contribution from our Chinese colleagues, the new planetary and lunar ephemeris called the Petrel 19 was developed and released last year by Tian 2023. And the work is summarized in the CMDA paper. The dynamical model is fairly similar to the JPL's DU4 study, but this includes the slightly different Earth tidal model. So moving on to the contribution from our French colleagues over the past, in the past triennial the period, they have looked into a better or improved way of modeling the KBO's dynamics, and also looked into the possible applications of using the Bepi-Colombo data for improving the planetary ephemeris. And they also looked into the machine learning, the methods to look into how you can provide improved constraints on the alternate theories of gravitation, and the Mariani et al. 2023 in PhysRapD provides a good summary of that. And also at the Journey meeting, they presented the modeling of the Earth's moon tides by updating the viscoelastic deformation of the moon model. It was work presented by the Baguet in 2024. And they also looked into the consistency of the ICRF3 under the presence of the galactic aberration, which was detected in the ICRF3. Okay. And lastly, in POP19A, the planetary ephemeris has been used to perform orbit determination of about 14,000 objects using the Gaia DR2. Now we're going to move our gears a little bit and start talking about the small body ephemerides. The small body community has adopted what is called the ADIS astrometric format, which is a lot more comprehensive and more robust way of sharing the astrometric information. This new format has been adopted by most major surveys, and we hope that the users will be adopting this ADIS format. And also the ESA Gaia mission has completed the third data release called the DR3 and the focus data release called the FPR. And it provides the astrometric observation for nearly about 160,000 objects. And this data has been ingested by the JPL Solar System Dynamics group to improve and update the orbit solution of the small body database that they maintain. And also the JPL Center for Neurosoptic Studies, CNEOS, implemented a improved way of monitoring the Earth's impact probability. They went from the linear, the baseline of variations, to the more capable and robust nonlinear Monte Carlo method. And more information can be found on the CNEOS website. Also continuing with the small body ephemeris, the small body assessment group, special action team compiled a report that includes the discussion of the effects of the Apophis 2029 April 13 encounter. They talked about the effects of the encounter, the scientific observations and observational strategies, as well as the hazard assessment for the spacecraft contact with the asteroid. And the PDF given here provides a lot more details should you be interested.
And also JPL successfully supported the DART mission by providing the firmware service for the Didymus and Dimorphos. And also the JPL is going to be providing the orbits for the Psyche, Lucian, Apex missions. And also the future activities involving the preparation for the upcoming operations of the Vera Rubin telescope and the annual surveyor missions are getting there, mostly by the MPC, JPL, NEODICE, and NEOCC. Just to conclude, the study of the planetary motion continues to be important for both the theoretical and practical purposes. And ESA's Gaia mission provided the substantially advancing astrometric observations that are both great in quantity and quality. And the NASA mission, NASA's DART mission was a paramount importance for the testing the deflection technology, and the major data processing systems are getting ready for the start of the operations of the Vera Rubin and NEO surveyor. And lastly, the adoption of the ADAS format will provide a lot more comprehensive way of sharing the astrometric information. And just like Brent did, I'd like to end with a brief advertisement about the 2025 IAU Symposium titled the Advancing Reference Systems, Ephemeris and Standards. And to one of your questions earlier, bottom right provides the key topics. And this symposium will be held in August of 2025 in Argentina. Thank you.
Thanks. Is there any question? No questions? Well, just to make a question. When you compare the different models, you mentioned the JPL model, the Russian, the Chinese.
Right.
I mean, what kind of difference you get with the models?
I mean, the difference really depends on the particular body. For the moon, the difference is a lot smaller compared to the Mars, for example. I mean, give or take, the moon we know is positioned to about a middle level. Mars we know is positioned to about a couple hundred meters. So it really depends on what data set you use and for what period of time you're comparing to. So last I checked, which was a few years ago, the comparison between the JPL, the Russian folks and the French one, they're all within a few times the quoted uncertainties. So they're in many regards comparable, but also depending on the applications.
Okay. Okay. Yeah. So if there is no other question, then we can continue. Thanks again to Ryan. Now, the next presentation is by Julio Fernandez, The Depletion of the Asteroid Belt and the Impact History of the Terrestrial Planets.
Well, good afternoon. One interesting question we might ask is how much mass is the asteroid belt losing at present? This will be the goal of this presentation, try to answer this question. First of all, we will make a distinction how we go. It's okay. We will, how we go back?
No, green is forward.
No, this is laser.
Oh, the other. Okay, that's okay. Let's go to the previous one. This one. Okay, thank you. Well, these are the goals of the presentation. Then we go to the following. How the asteroid belt is losing the mass. The mass is go under the form of macroscopic bodies, NEAs in particular, and the NEAs, finally, most of them will end up colliding with the sun. Part of the bodies also go to the outer planetary region, and they are ejected by Jupiter. By the meantime, before being ejected, can also pass through stages of NEA. But also part of the material that is lost by the asteroid belt is under the form of meteorite dust. We are going to make a distinction between what we understand as macroscopic bodies and meteorite dust. Macroscopic bodies essentially are, their dynamics is dictated by the gravitational perturbations by the planets and the Yarkovsky and York thermal forces. Thus, the dynamics is dictated by the gravitational forces by the planets and the Poynting-Robertson drag and the solar radiation pressure. More or less regarding sizes, macroscopic bodies, we understand bodies that are greater than 1 meter, approximately, much greater than 1 meter, and thus much less than 1 meter on the other, or macroscopy or some micron or some micron sizes. Most of the NEAs come from the inner and middle region of the asteroid belt. We can divide the asteroid belt essentially in 3 regions, inner, middle, and outer. They are divided by the 3.1 and 5.2 mid-motion resonances with Jupiter. What is the information that we have from different surveys? What we know now very well is the cumulative luminosity function NEAs, that is the distribution of absolute magnitudes. And from that absolute magnitudes, we can go through different steps to derive the size distribution of NEAs, and from the size distribution we can derive the mass distribution, and then if we integrate the differential mass distribution between convenient limits, we can obtain the total mass, the mass of the total population of NEAs. This is the result that we have there. And then we just put numbers into this equation. We obtain the mass that is the total mass of the NEA population. And if we take into account the dynamical lifetime of NEAs, we can derive from there the mass loss rate of NEAs. That is the result that appears below. Then this is essentially mass that is being lost from the asteroid belt, from the inner and middle part of the asteroid belt. Different simulations and numerical integration show that most of the mass actually is lost from the outer asteroid belt. Models show that about between 3 and more and 5 times more mass is lost from the outer asteroid belt. That means if we consider this mass loss, we will have at the end a total mass loss that is that we put the result below. M macro, mean macroscopic bodies, that is the result that appears there. That, as we say at the beginning, we have to consider also the mass loss under the form of meteorite dust. This can be derived from the observation of the zodiacal cloud. We have from different studies that we require between 5 and 10 tons per second of material, of that material, in order to keep the zodiacal cloud in a steady state. That means that this is a material that has to be incorporated. this material is supplied by essentially short period comets and asteroids. Then the unknown here is F, that is, what is the fraction of mass that is coming from asteroids? If we take as the mass that is required to keep the zodiacal cloud in a steady state of 8 tons per second, then a fraction F times 8 will correspond to asteroids. Then if we sum the contribution of macroscopic bodies, and thus we will come up with the result that is below. That is, it will be a function of the fraction F. Then we have the mass can vary a factor of 3 depending on the value of F that is adopted. If we take as a standard value 0.2, 20% of the material comes from asteroids. That many also try to convert to this value. Then we have the value of mass that is lost by the asteroid belt. Result appears below. Then we can make an extrapolation to the past. We have the mass that is lost by the asteroid belt at present. Bearing in mind that the loss of material will be proportional to the square of the population of bodies that we have in the asteroid belt, we can make an extrapolation of the mass that the asteroid belt had in the past and the mass loss rate in the past in the equations that appear below. Then we have these results. If we go to the past, how the mass of this asteroid belt evolved during the last 3.5 billion years. And we find well the standard value that we adopted for the mass that is lost by the asteroid belt, really the growth is very little. But it could be, if we just add, take a value a little higher, we, in this case, we
30 seconds to
exponential values, much greater loss or increase in the mass loss, and finally, very quickly, this will be more in line with what the geological record show with respect to the mass that have been lost. And finally, these are a summary of the conclusions, and thank you.
Unfortunately, there is no time for questions. Okay. So maybe at the end, we will have some extra time. So if there is any question, we can back to the end. Now the presentation will be by Sonia Fornacier, Eyes on Comets, Lessons Learned from the Rosetta Mission.
Okay, good afternoon. So you know that the Rosetta mission observed the comet 67P for more than 2 years. So here you have a typical spectrum of a comet, and you see that the spectrum is red with a broad band indicating a composition associated with organic rich material, polyaromatic compounds, and opaque minerals. The mass spectrometer detected more than 60 molecules, including glycine, that is the simple amino acid. So comets can indeed bring building blocks of life to Earth. However, the deuterium over hydrogen ratio is 3 times larger than that of Earth oceans. So comets like 67P didn't reach our planet of water. And finally, the dust to ice ratio is bigger than 3, meaning that the comet is dominated by refractories. So on the comet, we see composition and colors variety. So macroscopically, we distinguish 3 terrains. And actually, the one enriched in water ice and also found to be active are bluer in slope, means that the spectral slope is lower compared to the dark average terrain, while dusty regions tend to be redder. And concerning volatile, they are scarcely observed on the top surface. And we detect two kinds of volatile, mostly water ice. You have on the bottom left example of a water ice exposure that we detect directly on this nucleus, with size ranges from sub-square meter to the wider one that are on the bottom left side up to 1,500 square meter in size. And in the bottom left, you have a part of a new region. And in this region, Virtis spectrometer detected for the very first time and unique, the CO2 ice on a cometary nuclei. So you have the spectrum on the right side. So we monitor, thanks to the OSIRIS color images, over 3,000 sequences, analyze all the exposure of a water ice on the nucleus. So here you have a map of a comet with the name of the regions. And the points that you see in red, cyan, and green are exposed water ice detected pre, during, and post-perihelion respectively for the colors. So you see the distribution. We integrated the total surface of exposed water ice, and we found that it is only 50,000 square meters. That is about 0.1% of the total surface of comet 67P. So this definitively shows that the top layers of comet is dominated by refractory. And in case of a 67P, we see a dichotomy in the exposure of water ice distribution among the big lobe and the small lobe. The big one have 6 times more abundance water ice than the smaller one. And this give additional evidence to the fact that the two lobes actually have different mechanical and physical properties supporting the binary formation hypothesis for this comet. So how exposure of volatiles looks on the comet. So here you have a wonderful RGB image of a comet acquired by OSIRIS instrument on June 2016. The resolution was 30 centimeter per pixel. So this area comes from the Anu region that is in the southern hemisphere big lobe. And you have a canyon-like structure where you can see inside frost. You have several exposure of volatiles. For instance, this new scarp, the bright stuff on the up left position. But if you zoom in the image, you really see a lot of bright spots. So exposure of volatiles that are really tiny. So you have an example in this zoom, and you see that the water ice exposure are really sub-square meter sized. And locally, the water ice abundance can reach more than 30%. In this case, 46 and 75% in the two bright spots underlined by the blue arrows. So they are very tiny. We monitor actually the distribution in size of this exposure of volatiles. So you have here the equivalent diameter and the frequency. You see that they peak a very small size. And in particular, we look at the surface distribution pre and post perihelion for images acquired with a resolution better than 1 meter per pixel. And here on the center and at the right, you have the histograms. And you see that there is a huge difference in the median value. In the pre-perihelion exposure, you have a median surface for the bright spots of 4.5 square meters, while in the post-perihelion is only 0.7 square meters. So this is not related to different physical properties of a comet, because it's clearly an observational bias. During post-perihelion observation, we got really closer to the comet, so we reach the highest resolution. But the message is that when you have the good spatial resolution, the typical size of exposure of volatiles is of the order of a square meter of a sub-square meter. So you see the median is only 0.7 square meter. So, and you see that half of the exposure in the post-perihelion has an area that is a sub-square meter. So water ice is difficult to be detected directly exposed on the surface. It is tiny usually, but there are a number of evidence showing that water ice is very abundant just beneath the first centimeter of the surface. So to convince you a few proof of this, each time that we see on the comet cliff collapses or formation of new scarps, we see on the wall of a cliff collapse or within the scarps, blue and bright material that is clearly exposure of water ice. We have also evidence from outbursts. Here you have on the right a region that is called Imhotep. We see an outburst, and the region before and after show a new cavity in the wall. You have the bright and blue stuff that is water ice. And we have also indirect proofs from Philae. Philae landed on the comet 3 times on November 2014. And in the second landing, actually, the Philae lander stamped in a boulder for 25 centimeters and expose the primordial water ice inside the boulder that you see here in the movie, where we estimate a water ice abundance of 46% and a dust to ice ratio of 2.3. And finally, the fact that water ice is abundant beneath the surface is due to the fact that we observe both the diurnal and seasonal cycle of water. So here you have a picture showing the spectral slope of a comet acquired in June 2015, and the two images are separated only by 20 minutes. And you see that all the regions in blue emerging from the shadows, so from the cometary night, are bluer in colors, water ice enriched that condense from the subsurface during the cometary night, reaching the surface that is cold. And this same region, 20 minutes apart, when illuminated by the sun, you have the sublimation of volatiles and sudden changes in composition and colors on a large surface of hundreds of square meters. And together with this, we also see a thin front frost clearly moving in the images with the shadows. You have an example on the right side, even with images separated by 20 minutes. And finally, we observe the seasonal water cycle. Again, here you have images showing the spectral slope. This time they are separated by more than 1 year. So on the left, you have an image acquired 1 year before perihelion, and in the center, a few days after the perihelion passage. And you see that the spectral slope decrease of about 30%. And this is because close to the perihelion, you have the peak of activity that lift up the refractory mantle, the top surface that is dominated by refractory. And so we can observe actually the underlying ice-rich layers. So here the conclusion that just summarize what I say. So comets are rich in refractories, material, organics, and contains building block of life like amino acid. And if we want to send a cryogenic mission to a comet to get sample, spatial resolution is really mandatory to get the good region and to grab volatiles. Thank you for your attention.
There are time for questions. Yeah, go ahead.
So, thank you for the summary. Appreciate that. The detection of CO2 ice, were you actually looking for it? Because I'm curious why in other common observations, we haven't seen CO2 ice before. And is it just that we weren't looking, or did you get lucky? How do you think that happened?
I think so the problem was that the spectrometer Virtis and to operate in the far longer wavelength end of April, so before the perihelion passage, and the very first and unique detection of CO2 was a few days before it did. But I'm convinced that close to perihelion, we really would have observed much more CO2. And also an important stuff is that the refractory really dominates. So you should have good spatial resolution to detect water ice or volatiles like CO2 or even methane where the comet is very far away. Because the typical size of water is less than 1 square meter. So if you have a pixel that grab 100 meters, it's really difficult to have volatile exposure when the comet is actually dominated by refractory that darken a lot the compounds, the composition.
Okay, we have to move on.
So let's continue with the co-chair of the session. The next talk is by Gonzalo Tancredi, a survey of comets in the vicinity of Jupiter.
Okay, well, this presentation goes back 30 years ago. when I was a PhD student in Uppsala. But now my colleagues are from my institute in Uruguay, as well as colleagues from Spain, from the Instituto Astrofísica de Canarias, and the Light Bridge company. Back in 1991, we have the previous ACM in Flagstaff, and I made a presentation with the title, the vicinity of Jupiter, a relation to look for comets. The idea was based on this result from an dynamical study, where we compute the spatial density of comets in the inner part of the solar system, is the right one in the eccentric coordinates, but in the in the left one, and the right one, it's a plot with a spatial density, but in a frame where Jupiter is always at distance 1, 0, 0. So it's a reference respect to Jupiter. So you can see that there is a high density of objects in this point here. So the conclusion was that the vicinity of Jupiter is the region in the solar system where you would find more comets. It's simple to understand why it is. It's when the density, the highest density of a place is the entrance. And Jupiter is the entrance from the outer to the inner solar system. At the end of my presentation, I remember Gene Shoemaker was in the back, and he said, "What a great idea. We have never pointed the telescope to that region because we thought Jupiter would saturate the plates." My answer was, you should point a few degrees away from Jupiter. And then the rest of the story, you know it. In March 1993, Shoemaker and Levy discovered Shoemaker-Levy 9. The object was discovered. Well, this is a space watch image. I don't have the original Shoemaker's plate, but it looks like this. It's like a trail, but in fact, it was not a trail. It was a train of objects. That's the image, for example, from the HST a few months later. And then in July 1994, we have the impact of the train of comets. This is the collection of the MPC reports from those early days in 1993. And in fact, we were doing some observation from ESO, looking for comets around Jupiter, and our observations were just a few hours before Gene Shoemaker observation, although he reported first, and that's why it's called Shoemaker-Levy 9. So we decided to redo the observations and redo the calculations. In 1991, we used something like 133 comets, and now we have something almost 600, so 4 times more, and we find the same conclusion. Oh, sorry. The vicinity of Jupiter is the region 3 or 4 times more denser than any other place in the solar system. So that's the reason why to look for comets. And then there is another advantage, because there is a separation in phases, in velocity phase space. Asteroids move faster than objects around Jupiter, for example, the satellites of Jupiter that moves slower with a velocity similar to Jupiter. And then you have the TNOs and any other farther object moving slower. So if you make a set of images separated a few minutes, this is enough to make an estimate of the sky velocity, and then then it's possible to distinguish between the different objects, or even by stacking, you could increase the signal-to-noise ratio. This is the area where we would look for objects encountering Jupiter. These observations were done with the TTT project from Light Bridge. It's an 18-centimeter telescope with a large CCD. The observations were done in November and December 2023 at Jupiter opposition. In fact, Jupiter was at perihelion, and that may be another advantage that I will not have the time to talk. We made a mosaic of 13 by 11 fields in right ascension and declination, in total 143 fields, centered on Jupiter, covering something like 8 by 7 degrees, so something around 61 square degrees. For the reduction techniques, we use two different techniques. In the past, we were using plates. That was much more difficult. We have been using Tico Tracker. It's a software developed by Daniel Parrott, and it has many advantages. For example, it has the possibility to automatically identify the known objects. For example, all the dots there are known objects in the fields, in those fields. So it's also possible to do synthetic tracking, and it gives you the discovery via an automatic way with some probabilities, for example, high confidence, medium confidence, or low confidence. In addition, we have been also developing another technique using stacking and image segmentation. We stack the image with Jupiter motions, and the objects that are moving with the same velocity or similar velocity to Jupiter should look like points. And using some kind of image segmentation, we can separate points from lines or short trails. Those are the candidates that we have found so far. The green ones are candidates with high confidence, and the yellow ones candidate with medium confidence, and they cover, as I said before, the region around Jupiter. So we are not taking into account all the main belt asteroids. These candidates are taken from just one set of 4 images, but we have 2 or 3 sets of 4 images in different nights, so we can combine the information from one night to the other and to try to match the observations from one night to the other in order to get a better estimate of the orbit. So, for example, these are the plots of the position and velocity vector for the candidates. The colors in the left plots are from different nights, and the ones on the right are matches that we find in two consecutive nights or separated by a few days. Up to now, we don't have any good candidate. The candidates that we have this preliminary solution that we obtained then using Find Orb. It's typically a 2 or 3 day arc. It's not a good one, but it's, I think, possible to distinguish between objects in the main belt or in the outer part of the main belt corresponding to objects that are close to Jupiter. So up to now, we don't have any good candidates. These are main belters. Regarding the limiting magnitude, in the upper line, it's detected, the object that detected in a single images. In the middle one, it's detected by stacking, and in the lower one, those that are not detected. These are known asteroids that are in our field. So we can say something that the limiting magnitude in B filter could be on the order of 21 to 21.5. That's an important increase corresponding to our study in 1992 and 93, where we reach a limited magnitude of the order of 20.1. So it's an increase of 1 magnitude. So for the conclusions, well, we confirm that our 1991 results that the highest spatial density of comets in the solar system is in Jupiter's vicinity. By observing Jupiter at opposition, the planet encountering objects are separated in velocity space from main belt asteroids. We perform a new search covering something like around 60 square degrees centered on Jupiter. The results up to now have been presented using Tico Tracker. 60 unknown objects with slow motion were found, and preliminary match for 2-day observations plus orbit computation does not give any interested candidates up to now. In 1993, we, as I said before, we reached a limited magnitude 20.1. Now we are around 21.3. So one thing that we have done in 1991, and we are planning to repeat, is to make a new estimate of the total population of Jupiter family comets, because we know what is the density that we should expect. So if we don't find any object, we can make an estimate of the upper number of Jupiter family comets. And also maybe to look for precursors of impact flashes, because in November and December last year, there was some impact flashes on Jupiter.
Thank you. We should move on. We have no time for questions. So the next speaker is Stephen Chesley, Orbital and Physical Characterization of Asteroid Didymorphos Following the DART Impact.
Good afternoon. Yes, so I'm going to talk about one of the projects that came out of the DART impact. I think there's something around 100 papers so far from this mission. We were looking at the effect of the impact. We were focused on the orbital changes, and we found some other information. You can see a long list of co-authors. If you're not familiar with the DART mission, this is the elevator pitch. It was intended to be a planetary defense demonstration mission, hit the satellite of this binary asteroid system, change its orbital period, thereby demonstrating a possible approach to planetary defense. Launched in November 2021, impact less than a year later, September 2022. Spacecraft was around 600 kilograms at around 6 kilometers per second, and the target about 150 meters in diameter. And it worked. You can see on the left what the spacecraft saw coming in, followed by a loss of signal. So that was a pretty good indication that the impact was successful. And on the right, you can see the view from one of the Atlas telescopes, where there's this gas plume that came off. It was very obvious and very exciting to see this almost immediately coming in after the impact. So I want to emphasize Shantanu Naidu was the lead for this project. He and I worked a long time to get this. And here's the data set that we used to get the orbit of the satellite about the primary following the impact. Let's see. So we had mutual events starting from 2022 after the impact until 2023, plus, of course, a lot of pre-impact data that went in to inform the fit. We had radar range and Doppler offsets between the primary and the satellite, and we also had right ascension declination offsets, essentially optical navigation images from the spacecraft camera. And this is one of the optical navigation images. We were measuring the limb-to-limb positions there, and also estimating the size of the bodies as part of the fitting process, and thereby obtaining a center-to-center offset that we used in our fits. For radar, this is a typical delayed Doppler image. You can see there the primary and the satellite. And if we had not had the impact, the predicted position of the satellite is here in yellow, and you can see the track of the satellite in delayed Doppler space, and it's already about a quarter of a rev off, and this is after, I think, 10 or 12 days following the impact. Then the mutual events. That was really the key observable for this. And I can't talk about the mutual events without mentioning and emphasizing this was a huge effort, a global effort to collect the photometry. And that was documented in a paper led by Nick Moskovitz, Christina Thomas, with a lot of co-authors, because there were a lot of observers. You can see there at the top, straight from this paper, 224 light curves, 28 telescopes, 38,000 images, and over 1,000 hours of telescope time went into collecting that. And this is what we saw. This is one example of one of these mutual event patterns. You can see here, this is the brightness after the photometric signal from the primary has been subtracted. The blue points are the photometric points. The red points are what we consider to be the stop and start of these events. And so we were fitting the start and stop time. We distilled all the photometry down to a single time as an observable, actually start and a stop time as an observable. So there were 224 light curves. We had 270 start or stop times for these events. We also, being dynamics folks. We had a dynamical model. We used the planar full two-body problem, which is to say we have the primary body. We used a oblate spheroid for Didymos and an ellipsoid for the satellite Dimorphos. Very clear in the data was the apsidal precession. The line of apsides was advancing by about 14 degrees per day because of the J2 of the primary, and regressing by about 8 degrees per day because of the C22 of the satellite. That is to say, the ellipticity of the equator of the satellite. Okay, there's a long list of parameters that we were estimating here. I want to emphasize this A and tau, an amplitude and a time constant. We put in what we initially were calling, we're still calling a drag term, essentially a deceleration in the angular velocity of the satellite. And we get a solution. I'm not going to go through this. It's in the paper. A couple of things just to call out here. We were able to estimate the actual delta V of about 2.6 millimeters per second. We get pretty good numbers for the size of the satellite. And 32.7 minutes is the change in period immediately after the impact, and another 34 seconds in the months that followed. Also, this 1.3, I'll come to this. This is the axis ratio on the equator of the satellite. So first, here's our residuals before we figured out we needed this drag term. And there's this clear linear runoff, which tells us right away that the period is not constant after the impact. And if we add in this dissipative term in the angular velocity, we get much better residuals. So what is this? The idea here, and you can see on the right, the dust that's present in the environment as a function of time. This is from Teddy Coretta's paper. At the beginning, it's quite a lot, and down a month or two later, it's almost gone, even almost detached from the nucleus. So the idea is that there's this interaction between the binary components and the debris in the area, and that's leading to removal of the debris from the system, and that's going to remove energy and angular momentum from the binary orbit, which is going to collapse the orbit, lead to shorter periods. And so we found a time scale of 12 days, give or take 7, as the e-folding time for this debris removal, which is, I think, a pretty interesting result. And then you go to the Coretta paper, and they have this plot from the images, and you can see that there's clearly the same exponential kind of pattern that we had hypothesized and put into our model. And I went through in here with the ruler and found a time scale of about 9 days, which was pretty satisfying to see that the agreement between these two results. Okay, one of the other big things that came from this, I think, that our work we didn't expect, we could clearly see that Dimorphos had been dramatically reshaped by the impact of the DART mission. So the pre-impact images that were analyzed by Daly et al. Show that it's a very near a circular equator. You can see the axis ratio in the equator is about 1. And our analysis is at about 1.3. Now, this is a plus or minus 0.01, but that's a formal uncertainty. There's a lot of things, there's a lot of assumptions in our models that aren't quite right. Like I said, we had a planar problem, so there's no possibility of non-principal axis rotation. We're assuming an ellipsoid, not the actual shape of a body. And so these are formal uncertainties, but I don't think any way to slice it that there was a dramatic reshaping. But that's been corroborated by other results. So independent Dimorphos light curve modeling from Provis et al. Showed it's in the range of 1.1 to 1.4 for the axis ratio. And here's their key plot in that paper. Here's the real light curve. They subtract out the signal from Didymos, and then here's the signal from Dimorphos, plus these two mutual events that really aren't part of the problem. And you can see this very shallow sine wave here, which was not visible in any of the light curves before impact. And this wave has an amplitude that gives them this result. And the fact that that wasn't seen in pre-impact light curves, I think, really emphasizes the fact that this is a change from before the impact. Separately, and just from forward modeling, Raducan et al. Showed that for essentially for near zero cohesion, they found A over B as high as 1.2. And that's over here. In fact, and their conclusion was that this is where Dimorphos is in terms of cohesion. And you can see this, well, this is the side view, and this collapse on one lobe essentially gives you this reshaping effect. So we have, I think, multiple different directions show dramatic reshaping. Hera is soon to be en route, and we will get more definitive information. That's all.
Thank you. Time for one quick question and quick answer. If not, let's move on. Oh, just one.
Do you have any idea on what time scale it will convert back to its original shape? Is that like millions of years or?
No, I don't. But I know there's tidal dissipation in the excitation of the spin, which we think must have happened. That could already be apparent, possibly. I saw some work that already by the time that Hera arrives, some of the tidal dissipation effects in rotation. I don't know about reshaping.
Let's thank the speaker again. So the next talk is by Yongmin Jonan, Korea Pre-Earth Encounter Flyby Mission to Apophis.
Hello.
You may start.
Okay. Yeah, my name is Yongmin Jong-an, and the PI of the projects is Youngjun Choi. I talk about well, the disclaimer first. This contents I present today was the core framework of Korean Apophis mission as of early July. But the situation is changing rapidly. So, basically, this plan reflects CAS is the Korean Astronomy and Space Science Institute, which is my organization, work with APL, the Johns Hopkins University. And the content, the present today is largely developed with APS support. And many parts are borrowed by the APS own previous Apophis mission called FLARE. And for the Korean design, the design part was largely developed by the private company, Korean private company Satellite Initiative. And the recent changes is going on, and we realized the Ramses mission, which is the ESA's rendezvous with Apophis pre-Earth encounter, is very likely. And for this kind of development reduces our unique scientific value with just flyby mission. And also the funding situation is not clear, and the launching vehicle issue is still ongoing. So right now we are considering other different options, including collaboration with Ramses. So just consider the content present today is just one possible options we are considering. Okay. For this mission, there are two main objectives. One is for the scientific perspective, we capture pre-Earth encounter reference images to compare with post-encounter images from OSIRIS Apex. So you all know what the Apophis is, right? So it encountered with us in 2029, April 13th. So we focus on the surface change induced by Earth's tidal forces. For the reference images, we are capturing the color change before and after the Earth encounter. And for the planetary defense perspective, we focus on the rapid response and mass measurements. So we conduct a flyby mission to experiment with rapid mass measurement techniques. And these measurements to validate technique that could be critical in responding to potential future Earth threats. So orbit strategy, we place our spacecraft in a basically more like a cislunar space, and then wait there to encounter the Apophis. And we execute the chemical burn to intercept Apophis. And for the payloads, we utilize Dart Draco flight spare, which is free. Well, it is not free, but we cut the cost. And we also deploy 1 or 2 CubeSats to measure the mass by flyby. So the launching window, even the January 2029 is possible. And we release 1 or 2 CubeSats and with the X-band transponder, and execute a flyby of a few hours, 2 or 3 hours before, or even 10 hours before Apophis closest approach to the Earth. And we also use, for the camera, we use a scan mirror for the capture high resolution image. For the trajectory, where we do not have enough fuel, so we need a rideshare. Basically, we are considering there should be many lunar rideshare by the United States, like a CLPS. And we are hoping that, and then we consider many different options, and there are so many different possibilities. This is one single option. Here is the center is the Earth, and this is the Earth Moon rotating frame. And here's the Lagrangian points. So here is the Moon, and here's the Earth. We use gravity assist with the Moon, and then go far away, and then we use a staging orbit around L3 points, and then meet the Apophis here. So this is just one example. And because we use rideshare, the additional delta V is very small, less than 150 meters per second. And typical flyby speed is about 6 or 7 kilometers per second. So this is another example starting here. While we are going to the Moon, well, this is a rotating frame, so orbit looks very weird. And this is the trajectory of the Apophis. So we escaped the translunar orbit, and then go weird, go around the 3 to 1 lunar resonant orbit, and then meet the Apophis here. So there are several different options. For the mass measurements, we use a Doppler gravimeter technique, which was developed by NASA in APL for 8 years. It's basically tracking a CubeSats using the spacecraft and DSN during the closed flyby to the Apophis. So this kind of measurement is very tricky and very challenging due to the small mass of the Apophis. And we use an X-band radio transponder. And for the CubeSat, radio and dispenser will be purchased from the commercial suppliers. For the imager, well, this is the flight model in the garage of Dart Draco. And it will be modified to include color strips matching the apex wavelength bands. Basically, the V band already here and W band here in yellow to make a reference image. We considered several different options, but we concluded it's better to use color strips. Basically, the different parts of the CCD capture different wavelengths. And then it's modified. It's equipped with a scan mirror here. So it is rotating. The camera is fixed and the scan mirror is rotating. Basically, for the flyby mission, the rotating speed of the target is very fast. So usually you fix the camera and then you just see what you in the viewpoints, and then after several minutes or seconds, say goodbye. And if you have time, then you can rotate your body like 1 minute later, and then see very small targets. But basically, you fix the because you fix the camera. But here we use the scan mirror, which is developed for the Europa Clipper by APL. We can.
You have 1 minute left.
Very close to the target. Very close to the targets. So this is the overall design of the spacecraft. Interestingly, the Draco camera is inside of the spacecraft, and is opening hole here, and the scan mirror receives the lights through the opening. And it's a star tracker here. It's a reaction wheel. And this is upper view, and there's a solar panel here. I do not know the detail, but the total mass is about 350 kilogram, and you can see the dimension here is about 1,100 millimeters, so a little bit larger than meters. So summary. This is a key mission to capture pre-encounter data, and it provides a valuable comparison image for the post-encounter of OSIRIS-APEX spacecraft. And in the rapid response mass measurements concepts, we enhance the preparedness for the future annual stress with this kind of technique developments. So, yeah, that's what I want to say today. And then, as I mentioned earlier, that the presented concept is just one of the several options considered by now. Thank you.
Thank you. Unfortunately, we have no time for questions, but we can discuss. You can discuss with the speaker during coffee break. So we move to the next talk. We thank the speaker again. So the next talk is by Gulchera Kokirova. Apologize if I misspell. A family of asteroids with comet-like orbits associated with the Delta Cancridis meteoroid stream. Please go ahead.
Good afternoon, everybody. Let me start our presentation. Main approaches which were used in our study are the following. Activity of comets or their destruction are mainly responsible for formation of meteoroid streams. Second, when meteoroid stream crosses the Earth's orbit, meteor showers are occurred. Third, a presence of certain number of dormant comets, nuclei of dormant comets in the near population is not in doubt. By the ground-based observations, extinct-cometary nuclei outwardly do not differ from asteroids. However, they may be distinguished by dynamical properties. Typical comet-like orbit of an object implies that it has a cometary origin, and defining related association of such object with active meteor showers will significantly strengthen this assumption. Several asteroid-meteoroid complexes were identified using these approaches. We have continued this investigation and present results of finding of related objects in the delta concrete meteoroid stream. According to IAU MDC meteor shower database, delta concrete meteoroid stream is producing 3 confirmed meteor showers, and 1 shower has not been established. Besides, these 2 NEAs are indicated as possible parent bodies of the stream in this database. We searched for objects associated with the stream among near-Earth asteroids discovered before 2018 and identified new asteroids related to this stream. And also we have established northern branch of daytime shower and result presented here. Research method is based on above mentioned approaches, and it should be added that if an asteroid is in fact dormant comet, then it could form a meteoroid stream at the period of a past cometary activity. This meteoroid stream presently may theoretically produce meteor showers observable on the Earth. Orbits of these theoretical showers can be obtained from the results of calculation of orbital evolution of a proposed parent body. Asteroids moving on comet-like orbits and crossing the Earth's orbit are subject of the investigation. This run parameter is using for classification of orbits type. Condition of intersections with Earth orbits was checked in the NEO-DIS database. Using database NEO among NEOs discovered before 2018, we identified a number of asteroids crossing the Earth's orbit and moving on comet-like orbits. Because of this, these objects may represent the nuclei of extinct comets. Main parameters of these asteroids are summarized in these orbits. And as you see, 4 from them are classified as potentially hazardous ones. We calculated orbital evolution of these asteroids using Everhard Radau 19 method for the time interval embracing 1 cycle of variations of perihelion argument. As a result, it was found that all these asteroids cross the Earth's orbit 4 times during this period. It means that sizes of the heliocentric distances of ascending and descending nodes of asteroids orbits have values equal to 1 astronomical union 4 times, 2 cases at each of nodes. Variations of heliocentric distances of asteroid orbits on dependency on a time and argument of perihelion demonstrate figures 1 and 2, where straight line indicate Earth positions. And intersections with the asteroid orbit are indicated by the arrows. You can see 1, 2, 3, 4. These graphs are similar for all considered NIAs, so plots only for pair of them are presented at these plots. When we calculated coordinates of theoretical radiance, velocities, solar longitudes, and relevant dates of activity of theoretical showers using a set of orbital elements which corresponds to the Earth's crossing positions found from the calculation of orbital evolution. Then automatic search for theoretically predicted showers was carried out in all published catalogs of the observable meteor fireable showers, detected fireable meteors, meteorites, and so on. Under a comparison of theoretical and observable parameters, we required fulfillment following conditions for closeness of radiance, velocities, date of activities. A closeness of theoretical and observable orbits was tested using a very known the criterion of Southford and Hawkins. As a result of research, it was found that all NIAs have close association with meteoroid stream generating nighttime northern and southern delta concretes and daytime southern He Leonids. The result of a search for asteroids 1991 AQ presented at this table, and for asteroid 2003 RV11 are presented in this table. For the rest asteroids, results of outcomes are identical. As I was mentioned, a northern bridge over daytime shower has not been established. Our results suggest that this may be the Tau concrete meteor shower. As you've seen from this table, values of the criterion of Southward Hawkins confirm a closeness of comparing orbits, and a closeness of radiant position, velocities, and date of activity also point to closeness of observable showers to theoretically predicted ones. So when fragmentation of asteroids
30 seconds left.
and comets into large fragments occurs at low ejection speeds. And when we're establishing a connection of objects, it is necessary to study evolution of orbit and find the moment of their greatest similarity. If such similarity is found, then this moment can be taken as the moment of fragmentation. To establish moments of great largest orbital similarity, we calculated two criteria of similarity, the criterion and simplified criterion of Usher et al. Between orbits of studied NIAs, and followed this behavior backward over 12,000 years. So some cases of secular variations similarity criteria for asteroids between which, in our opinion, fragmentation have occurred are presented in this figure. And where the period of possible decay is indicated by sickles.
Please go to the conclusion.
So figure 4 presents a possible mechanism of parent comet breakup. This parent comet start break up more than 12,000 years ago. And then we start from two big asteroids. Next, cascade division they into fragments began, and this figure schematically presents this process. So, and my conclusion, so that a new delta concrete asteroid-meteoroid complex is established, which includes the meteoroid stream producing active meteor showers. Besides related association of certain near-Earth asteroids with the complex is found. We can consider this asteroid as the extinct fragments of a parent comet of this stream. Thank you very much for your attention.
Thank you. Unfortunately, there is no time left for questions. If any, you can speak with the speaker during coffee break. So I think we ended it.
Yeah.
The next session is at 3:30, always here. Yeah.
The last session of the division day.
Let's thanks all the speaker again.
Okay, I think we can start. We start the last session on on F division. And the first presentation, this last session, is by Dee Becker on Juno exploration of Jupiter's moon ring system and dark side.
Okay, thank you. I'm going to be showing you the view of the Jovian system from Juno, from its Stellar Reference Unit camera, or the SRU. And the SRU is actually an engineering camera on Juno. It's the spacecraft star tracker, and it's a low light, high resolution, visible wavelength imager that was designed to detect dim stars to aid in navigation. But the Juno project has been using the SRU as a low light visible imager to do some extra science at Jupiter. This figure is showing the Juno trajectory, and it's a very unique trajectory. It's the first polar orbiter. We come in over the north pole of Jupiter, have a very closest approach to the planet. It's about 3,400 kilometers. And then we exit from the south. And as the mission is progressing, the orbit is gradually evolving so that we cross the equator inbound, closer and closer to Jupiter. And this has allowed us to see the Jovian satellites at close range and also Jupiter's ring system. At this point in the mission, in the extended mission, the closest approach to the planet is on Jupiter's dark side. We did a lot of detection of lightning with the SRU during the prime mission. During the extended mission, we're extremely close to Jupiter, and we're able to do lightning detection at resolutions as high as 2 kilometers per pixel. Now, because we have a very high resolution vantage point, that also comes with a small field of regard. So as of now, there have been no extended mission lightning detections. But in the meantime, because of moonlight shining on the cloud tops, we're able to see the Jovian cloud structure, the storm activity, and in some cases, when we're very close to the terminator, we can see high altitude hazes being picked up by the SRU. So even though we haven't detected any lightning flashes in the extended mission, we have detected something pretty interesting. This happens when we're looking at the dark side close to the equator. And the geometry here is that even though we're looking at the dark side of Jupiter, the spacecraft itself is not yet in eclipse. Sunlight is coming from the side orthogonally. And what you see in this image is what we believe to be ejecta from little bits of Juno that have been impacted by the dust in Jupiter's ring. So this is a very interesting signature. We see it repeatedly. And we also have a waves instrument, electric and magnetic waves instrument on Juno that detects dust impacts on the spacecraft as a voltage impulse. And the waves instrument sees or is able to hear the dust impacting Juno at the same time when the SRU is imaging this ejecta coming off the spacecraft. The green dots in the figure are showing you the locations where we have positive detections of this dust with the SRU. The blue regions are places where we have a null result, even though we're taking long exposure images. And so where we're seeing this dust is between 1.2 and 1.345 Jovian radii, which gets us inside the Lorentz resonance at 1.4 RJ, which is where traditionally the ring dust has been very difficult to see optically. So Juno's adding to this data set, and we're continuing on. Juno doesn't just take data looking at the planet. The SRU also takes images looking out. We turn Juno out. This is one of our extended mission images of the Jovian dust ring, looking at the dust ring from the inside, looking out. And that's a vantage point that no other spacecraft has ever had before. What you're looking at in the picture are the two bright bands in the middle are the region of the main ring where the shepherd moons Metis and Adrastea carve out that high density particle region. A little bit further down in the image where it gets a little more diffuse, that's still the main ring, but a little more diffuse. And then further down is the halo region where the ring sort of puffs up and the density of the particles gets very low compared to the main ring. And we're seeing dust signatures even further in. The resolution of this image was 38 kilometers per pixel. Another opportunity to look at the ring is in our departure as we're exiting Jupiter from the south. And this is again the main ring and halo region. And the reason the lower part of the image is blacked out is because Jupiter's shadow is being cast across it. And the advantage of that is that for such a very dim signature, having that sharp dividing line allows us to see how far in we're continuing to see the dust optically. And so here again, optically, we're seeing the dust inside the 2-to-1 Lorentz resonance at 1.4 RJ. From the WAVES data from the prime mission, we know that those dust particles are probably on the 1 micron size. So we're assuming that's what we're seeing with the SRU. Another special guest star is the shepherd moon Adrastea, which you see there, which is almost at the outer edge of the main ring. Now, during the satellite flybys, it gives us the opportunity to take one image with the SRU per flyby because SRU images take a long time to be collected and we fly by the satellites very, very quickly, several tens of kilometers per second. And because you can't image a sunlit moon with the SRU without saturating it, we do the trick of imaging the night side using scattered sunlight from Jupiter or Jupiter shine. And that's what's providing the illumination here. We're particularly excited about the image that we took of Europa, which was Juno's highest resolution image of Europa at about 250 meters per pixel. And what we found in this region were areas of ice shell disruption known as chaos, where we potentially have a situation where there is subsurface liquid water. We also see potential plume signature stains next to double ridges. And so this image is giving a very high quality baseline for the upcoming Europa Clipper and JUICE missions to look for signs of the conditions that are favorable for life. Now, in December, right before New Year's, we flew by Io, and the SRU took an image of Io as well. This is Juno's highest resolution of that volcanic moon. And the region that's featured is the Zalmontes Patera complex, which is a region of tectonically influenced volcano formation. Now on Io, mountains are not themselves volcanoes, but they tend to be associated with volcanoes. And the theories for how mountains form on Io usually involve some form of very deep thrust faulting, where the surface is compressed due to this constant laying over of volcanic material from the volcanoes that are erupting material into the air. And as that thrust faulting occurs, that potentially creates a conduit for the magma to allow it to escape to the surface. And that's the main idea for how volcanoes come to be on Io. We do see volcanic change in this particular region. What you see on the left is the highest resolution Galileo data of the Zalmontes Patera complex. We do see new flows coming out of this Patera, and those flows where I've written new Patera
You have
branch
1 minute.
are hugging the mountain boundary. Anything dark is a very fresh lava flow. And the SRU being a very red sensitive detector, it can also detect thermal emission. And so we're seeing active lava. This is also seen by our infrared imager, GIRM. And what's intriguing to us is that we're seeing lava that is coming right from the base of the mountain. So whether there's a source vent there or not, we can't say at our resolution, but it allows us to further explore this relationship between volcanoes and mountains on Io. Thank you very much. That's a little sampling of what we've been able to do, and I'm happy to take your questions.
I'm for a short question. No question, comments? Okay, thanks a lot. Thank you for that. Okay, next presentation is in remote by Glenn Orton on results of observation of the Jovian system by Juno and the network of Earth-based astronomical observing stations. Are you?
Hello, I have a pre-recorded video.
Yeah. Just one moment, they are putting your presentation.
Okay. Hi, this is Glenn Orton from the Propulsion Laboratory. I want to
Okay,
introduce
is there?
ways in
You can
which
start.
mission science return is being Good. executed in collaboration with
Sorry, can you start again?
stations. The Juno mission is a spacecraft is a spin stabilized insertion 2016. It's an elliptical polar orbit. So the period began 53 days. It's now 32. Most of our data are taken from the Jet Propulsion Laboratory. I want to introduce you to the ways in which the Juno mission science return is being expanded and enhanced in collaboration with a network of Earth-based astronomical observing stations. The Juno mission is a spacecraft is a spin stabilized insertion from 2016. It's an elliptical polar orbit. So the period began at 53 days. It's now at 32. Most of our data are taken within 2 hours of closest approach, which we call the perijove, and that perijove is drifting north with time. Mission objectives include using the water abundance, determining Jupiter's O/H ratio to constrain its core mass and understand its formation better, understand the interior structure and dynamical properties by mapping its gravitational and magnetic fields, characterizing the three-dimensional structure of Jupiter's polar magnetosphere and aurora, and to map variations in the atmospheric composition, cloud opacity, and dynamics to depths greater than 100 bars at all latitudes. And that depth reach is being enabled by an innovative experiment, the microwave radiometer. How do we do this? A motivation to extend and enhance Juno science is made by providing spatial coverage over areas Juno is not observing, providing a context in time to track evolution of features Juno is measuring, covering spectral regions not included in Juno instrumentation, such as X-ray and then infrared, getting simultaneous coverage of multiple components of the Jovian system, chiefly how IO volcanism is affecting the magnetosphere. Our ground-based telescopes on our support team is shown on the map, plus Earth proximal like James Webb and Earth orbiting like Hubble facilities. We see contributions that listed here from over 60 different observing groups from X-ray through the radio. Plus, as I'll describe later, significant contributions from the amateur astronomy community. We're coordinating programs using an interactive Google table. Observers who want to contribute are invited to add to the table. The table consists of the spectral regions we're observing, the PI, the facility, and the instrument we're using, a description of the data, and the data schedule or data are requested or are assigned or successfully observed. This is mirrored publicly in a non-interactive table that's shown in this URL. Some examples. Even before Juno reached Jupiter, the particle appeal experiments detected a solar wind shock impinging on the planet. We noted that on that date, May 21st, 2016, Hisaki science, which measures both EUV aurora and thermospheric heating from the near-infrared H3+, is coincident with Juno's detection of a solar wind shock. Johnny Nichols and all also detected this in solar radiance associated with Hubble STIS observations. In fact, Johnny reported this was the highest auroral brightening he's ever recorded. This is all consistent as well from X-ray auroral observations by Will Dunn and company, noting that the X-ray aurora was far more compact and 40% brighter on May 24th, a few days after this shock impingement, than it was later, just a few days later on June 1st. For the neutral atmosphere, I'm showing you what results from Perijove 19 when the spacecraft was aligned in a new way so that the microwave radiometer could map much of the planet. We saw two interesting vortices. One vortex at 19 degrees north showed a colder region going from 0.7 bars down to 9 bars and its surrounding region, and then below it channels up deep, look deeper than the 9 bar region. It was warmer. JunoCam, our onboard visible camera, was not able to reach this region, and so we were lucky that we had Hubble observations that showed us that this was indeed an anticyclonic white oval. Another region, 38 degrees north, had just the opposite characteristics. At 0.7 bars on the 9 bars, or just at 9 bars, it was warmer. From 9 bars down deeper, down to 240 bars, it was colder. So you might think this is a cyclone instead of an anticyclone, but our Hubble image showed us a dark patch. What we did then to start verifying that, to confirm this, was we took data on May 29th, about a month and a half later. We had observations from the Subaru telescope's cooled mid-infrared gamma spectrometer complex instrument, discrete filters. We see these here. That 38-degree vortex is shown at 20.5 microns, sensing temperatures at 0.3 bars. So it tells us simply that the vortex is indeed warm compared with the surroundings. At 8.7 and 10.3 microns, which is sense 0.2 to 0.4 bars, we are sensitive to temperatures plus the absorption by ammonia gas and ammonia condensate. And that warmer means less ammonia and less condensate opacity, and that's all consistent with cyclonic downwelling of dry air. So in fact, this confirms the fact that this is indeed a cyclone. I note that 19 degrees north is hard to resolve, but the results we have are not inconsistent with its characterization as a cyclonic upwelling with an upper level colder brightness temperature. Contributions from the amateur astronomical community have a large cadre of observers, some very accomplished. There is immense interest in this group and a chance to get involved in the NASA mission. There's lots of motivation to do this together. This community, which is spread throughout the globe, can provide 24/7 coverage of the Jupiter system, primarily for the atmosphere. One easy thing that they can do is show us where we're not looking. Here's an example for Perijove 35. Here's a composite of JunoCam images at very high resolution, but only part of the planet. The rest of the planet in this map by Andy Casely did his own and 4 other observers composite here that in fact shows us that, for example, this region of sort of Rossby-like waves at the southern part of the South Equatorial Belt is a part of a large wave structure that continues on the rest of the planet. Whereas this series of anticyclonic white ovals really is just clustered here rather than distributed throughout the atmosphere. This example again shows a discovery made by an amateur astronomer, Clyde Foster, who was observing from no less than a Centurion in South Africa. He's using a filter at 890 nanometers, which is centered on a methane, strong methane band, which is sensitive to high altitude particles. And so we named this spot after him. 2 days later, we saw this with JunoCam, which looked like it's a very filamentary feature. And our resolution allowed us to show that this wasn't just a bright spot, but sort of a bilobate structure with 2 walls surrounding high altitude material. Amateur observations showed that Clyde's spot had then become a very dark region, and then a little bit over a year later, we caught it with JunoCam once again, and shown that it had turned into a cyclonic region that was, in fact, very chaotic. And we note some of these elsewhere in the atmosphere. We call them folded filamentary regions, and that's what Clyde spot has turned into. We look at longer wavelengths from the ground, from the Infrared Telescope Facility by NASA and Gemini North, 5 microns, which is a thermal emission sensitive to the temperatures of cloud tops. We note that these bright regions, which mean that they're warm, they're bright because they're deeper clouds in the warmer part of the atmosphere, correspond to the regions that are darker in the atmosphere. This folded filamentary region. So we have a nice tomography of the clouds that otherwise we would just think of as color changes. This also is true bright regions in the regions surrounding these anticyclonic white ovals in these dark spots. Turning our attention to Io, we note that, complementing Juno's close flybys last December and January, Kurt Rutherford and Fred Bagenal have been leading a program that coordinates Hubble and James Webb Space Telescope observations of Io. We can see here they resolve Pele and Patera, and they've as an example of a single pixel spectrum that shows the possibility that they may be able to map sulfur for and across the planet. This is in its early stages, and we'll be interested to see what comes out. A longer program that has been going on, headed by Jeff Morgenthaler since 2017, is using quasi-autonomous choreographic observations of Io in what is called the Planetary Science Institute's Io Input-Output Observatory, the IO-IO. We can see sodium nebula changing the wavelengths. We can see the Io plasma torus. So it's interesting to monitor volcanic activity by these in this method and understanding the global influence on the magnetosphere. So there are only a few of these many ways observations supported to continue to support the science output of the Juno mission. I invite any questions or comments, post them on comments or questions on Slack, or directly contact me at this email, glennorton@jpl.nasa.gov. I'll try to get to them as quickly as I can. Thank you very much. Thank you very much.
Okay.
Thank you. That turned out well.
The next presentation by Jack Connerly. So you have the green light for 8 minutes. The yellow is for question.
Which button?
They have put green button for the
Green button. Okay, my name is Jack Connerly. I'm going to tell you about the largest dust detector ever flown in space, Juno spacecraft. The concept is really very simple. The magnetometer investigations have 4 star cameras that are designed to do attitude determination at the magnetic field sensor. The guy that designed that instrument is a clever guy, and he said, well, I'm going to look for an asteroid too. So anytime something passes through the field of view 5 or more times in a sensible way, I'm going to record its time tag, its declination, inclination, and intensity. Maybe we'll get lucky and see an asteroid. Well, bottom line is, we didn't see an asteroid. What we did see were spallation products ejected from the body of the spacecraft by the impact of an interplanetary dust particle. Now I'm talking about dust particles of the size of about 10 microns, much larger than any collected by the dust instruments that are flown specifically for that purpose. They just see the small submicron particles from interplanetary space. Okay. If I can make this move. It's not moving. Here we go. All right. This is the count rate of the interplanetary dust that we observed during our mission. The upper right is the part of our mission from the deep space maneuver in towards the Earth flyby. So that's all in the ecliptic plane. We turned this instrument on, this detection mechanism on, as we were leaving the asteroid belt. For a few weeks, we saw absolutely nothing, which is what we expected. When we passed the 4-to-1 mean motion resonance with Jupiter, we suddenly started detecting a lot of objects, hundreds of objects. You see that in the yellow trace. We detected so many, we filled up our memory. And so the instrument would fill up its memory in the course of 8 hours or a day, and then there'd be a gap while we waited for the next telemetry downlink. And that's why there are gaps in this record. But as you can see in the ecliptic plane, we're getting order 100 impacts per day. Interestingly enough, we don't see any in the time segment right before the 5-to-1 resonance with mean motion resonance with Jupiter as well. After the Earth flyby, and that's the bottom trace now, moving from left to right, we were out of the ecliptic at about 5 degrees inclination to the ecliptic. and we saw about 1/3 as many impacts on the spacecraft per day. So that tells you something right away. It tells you that this dust is not brought into the solar system by comets and asteroids on elliptical orbits. The reason being is you circularize that elliptical orbit. It can't get past that 4-to-1 mean motion resonance with Jupiter. The source of this dust has to be between Earth and the 4-to-1 mean motion resonance with Jupiter. So it turns out, with the observations that we detected, the first of their kind of particles of this size, 10 microns or so, and the assumption that these particles enter the solar system with the inclination and eccentricity of the planet Mars, we have a primary distribution as indicated in the light blue. That consists of all of the dust particles that fill the volume traced out by Mars in inclination and eccentricity. Mars has a very eccentric orbit. And then, of course, they move outward and inward under radiation pressure forces and Poynting Robinson. That's a primary distribution. The other distribution you see, the secondary distribution, is due to an interaction with Jupiter. It's called the Kozai-Lidoff effect. You trade eccentricity for inclination, and that disperses the primary population into the secondary population. So when we did this, we thought, well, gee, this is heresy, of course. It's going to be very difficult for people to accept it. Let's look at the zodiacal light. The zodiacal light, of course, has been measured for decades, and it's got these odd peaks in it at plus or minus 1.3 and plus or minus about 10 degrees. For a long time, attributed to a couple of very special asteroid families. We take our distribution and compare it with the latitudinal variation of zodiacal light you see in the white trace. Sure enough, that distribution, determined by nothing more than the inclination and eccentricity of Mars, matches every single peak in the latitudinal variation of zodiacal light. Even that tiny little one near 20 degrees, where people are searching for another asteroid family. So that's the bottom line there. I would like to move on because we got some other interesting observations. This is the traverse from the asteroid belt out now to Jupiter. And you see the most significant thing we saw, in spite of the fact that there are very few interplanetary dust counts of this size on the way out, we saw this enormous spike in the data in December of 2015, about 6 months before our encounter. And we said that that has to be the tail of a comet. Got to be. What else could it be? In fact, this is a high resolution look at that. And you can see every day we got any tens or hundreds of counts for a period of an entire month. Had to be the tail of a comet. Now, so we looked through all of the known comets in JPL's database. And the way you do this is very simple. All the forces on this dust are radial. So it's just gravity and then radiation pressure force. So the dust is not going to migrate very far from the orbital plane of the comet. So what we did was we looked at every comet, and at the time we crossed the orbital plane of that comet, how far away is it? What's the distance to that comet? Most of them are way out of scale, but there are a few candidates down there. Unfortunately, we didn't match with any of them. Actually, going back, we do find elevated counts associated with some of them. But about a year later, we looked at the catalog again, and another comet appeared in JPL's small body database. There's 3,700 entries in it. And in fact, that was our comet, 1003641. We actually discovered it, but of course, the people that observe it enough to get its orbital elements are the ones that attach their names to it. So this is a plot of the distance between Juno and the comet as a function of time, and the distance in blue between Juno and the comet's orbit plane. And you can see that we passed through this tail just after we went through the orbital plane of the comet, which is what you expect. The velocity of ejecta of the comet material is actually quite small, compared to orbital velocities. And so you're going to find it near the orbit plane of the comet. Knowing the trajectory from JPL's small body database, we're able to do some interesting science on this now. The comet's trajectory is shown in blue, perihelion, January 2nd of that year. The Juno trajectory is shown in white, and where Juno is above the plane of the comet, we have a double width line. Where it's below the plane of the comet, we have a single width line. And you can see just after we pass through the plane of the comet, we saw the comet dust. In yellow, red, and blue, you see the trajectory of dust particles that we've calculated for a small ejection velocity, going back as far as 900 days before we pass through the tail of the comet. I'm going to blow that up a little bit so that you can see the left-hand side. The red, the blue, and the green are just three different particle beta. The particle beta is simply the ratio of the radiation pressure force to gravity. So 3.5%, 5%,
30 seconds.
6.5%. All of the particles of a particular beta appear on what's called a syndyne. So we can identify the dust particles that we detected as having a particle beta of about 0.04. The distance from the orbit plane gives us a good handle on the escape velocity of the dust. It's of order 100 meters per second, and it was ejected about 2 years prior to our passage through the comet tail. So that's how Juno acts as a cometary dust spectrometer, gives us a very good handle on the particle beta, gives us some insight into the velocity of ejection of the dust from the comet, and per Whipple's formula, the size of the comet, which is very difficult to determine otherwise because it just appears as a big coma in the sky. Thank you.
Thanks a lot. We are sorry, but we are over with the time, so we have to move to the next presentation by Hans Degg on photometric follow-up for the Plato space mission.
That's the green button, but you must bring it up, right? Someone? Okay, here it is. Okay, yeah, apparently we changed now over to exoplanets. And this is not so much a science presentation as a call for participating in a program of follow-up observations for the ground-based follow-up for the Plato space mission. This sub-program within Plato is led mostly by these three people you see here. And there's also a dedicated Plato working package there. Just in brief, Plato has been mentioned before. It will detect exoplanets with transits with a focus on observing, detecting planets around normal main sequence stars and up to as small as Earth-like and as with orbital periods as long as 1 year maybe. So we can talk about the habitable zone as well. And something that's special about Plato is that it has a strong focus and principally about half of the mission is dedicated to the study, the host stars also by astroseismology using the same precise, ultra precise light curves. It's an ESA mission that will be launched in about 2 years and operate for 4 years. It has a very large field of view, and you can see that as a dark blue area there of about 43 by 43 square degrees. And you see, by the way, the Kepler field as a small orange area in there. So it's about over 10 times larger than the Kepler field. The first pointing will be in the south in the first 2 years. And that is the only pointing as for now that has been decided. And with centered on minus 44 degree declination. No? Okay, I'll go over that extremely quick. Plato is basically a follow-up and a consequence of previous missions. Yeah. I cannot adjust anything. Oh yeah, no, it's getting. I have to go farther away, maybe. Yeah, closer. Okay. Okay. Yeah, yeah. Well, it's for now will be also the last mission that will do exoplanet transits, and that it we hope will do in a way that can be considered as a definite exoplanet transit mission. The transit method you know, but maybe some people who are not really from Division F listening to that will not know it. So what we observe is the brightness change of the star when the planet goes in front of it, and that brightness change is on the order of 1% typically or less, and it repeats with every planetary orbit. And one issue that has been with exoplanets transit detections since the earliest surveys is that we have the problem that we are not certain what we have observed. Is it a target star with a planet when we observe these repeated little dips, or is it a target star where nearby there's an eclipsing binary? And you will see then the same. And from the light curve itself, it's not possible to distinguish that. These cases we typically consider as, there are several terms for them. I usually use contaminating eclipsing binary CB. So how can we separate these? And there are basically two options where you can do radial velocity follow-up, which is great if one can do it, where you measure then also the mass of the planet, but often that cannot be done or is unpractical due to the small mass, for example, of the exoplanet. And the other one is to reobserve with higher spatial resolution. So if you do that and it's a true target star with a planet, you will get about the same light curve. But if you have these two objects separated, you will see a deep eclipse on the for the eclipsing binary. And these flux variations on the eclipsing binary, they are between 5 and 50%, and that is well detectable from ground observations. Whereas the transit itself might be detectable from ground or not. Typically, it's very difficult. So the issue is that the spatial resolutions of the space surveys are fairly large or fairly poor. Plato has 15 arc seconds spatial resolution. TESS currently has 21, and the previous missions also had several arc seconds. Whereas from ground, you easily get to 1 to 2 arc seconds spatial resolution. And here you see a comparison of images that was from the previous cohort mission, where you'd see on the left this, the image from the space mission, and on the right from a fairly moderate ground-based telescope, an 80-centimeter telescope. And so we attempt to find these eclipses, if they are really there, around any of the nearby stars. And that's what we have to do. We have to reobserve the transits from ground and observe also or measure the nearby fainter stars around them, which we can separate, whereas we cannot separate them in the space mission. Besides that validation that I've mentioned, there are several other objectives from reobservations, but I think they are a bit secondary to the validation of the planet candidates, but also finding TTVs, for example, when we reobserve later, maintain ephemeris for long-term reobservation. So there's a ground-based program that is led by Roy Alonso, and it has several working packages, and the two relevant ones are with the blue arrows there. There's one for the citizen science and the citizen scientists, amateurs, for their involvement by Günter Wuchtel in Austria that is led. And then the other one is for the other packages basically are for the professional contributions. And so we are preparing that now. We define the procedures, the software to be used. And once Plato is up, we will, of course, do also the actual observations and then coordinate these. The issue is now with the first Plato observing field was not that long ago decided to be in the south. It's centered at -48 declinations, and it ranges from -17 to -80 in declination. So only observers really that are south of -20 southern latitudes can cover well the whole field. Near the equator, most can be observed, but the southern part not really well. And from our large observatories at the Canary Islands in Hawaii, we can only observe the northern part. It's fairly marginal. Also in the exoplanet transit database, that is the current main database for amateur contributions. We have lots of contributions from northern latitudes. You see the geographic latitude of the observer, not of the object, down there in orange. Just look at the orange bars, and from the south, only relatively few, about 15% are coming from the south currently, and I think mostly from Australia. So to get involved, we look basically for contributors on all levels. Depending on their experience, they will either be more assigned to the citizen science follow-up or to the professional follow-up. And in general, they should have a telescope of about 30 centimeters that is fairly well available for observations that last at least a half night typically, or a full night. But even if you have a fixed schedule, we expect that about every night there will be some interesting candidates to reobserve. We have recently reviewed the software that's there to analyze these types of data, and we will likely support AstroImage J and MuniPack or MuniWin to do the analysis of the data by the observers themselves. One I learned about here in the GA is also something called Black Hole Tom. It's an online analysis tool, and we have to review that. And in any case, we will make available cookbooks for these types of reductions. And to the right, you see an analysis on a sample observations made with AstroImage J, and the black curve you see, that is an eclipsing binary that was around a planet candidate from the old Korot mission. So it was a false alarm. So getting involved, and I'm coming to the end with that. First, further information on Plato is generally, just Google for that. There's one separate page that is more with the scientific information for scientists. And then in the photometric follow-up, there's for one a paper myself and Roy Alonso wrote, easy to find on ADS. And then a form that is it's just a declaration of interest. It's not anything obligating to you to participate in, where we really compile the information by interested people, what level they are on, what support they would need, what instruments they have, of course, how much time they might have, and so on. So if you're interested, please go to that link or just talk to me there and I can send it to you. Well, thanks.
Thanks a lot. We have time for one question. Okay, on the web, no question, so we can move.
Can move to the next one. Is from John Subjak, from giant planet to brown dwarf, evidence for the deuterium burn in old age. It's a question.
Okay, first of all, I would like to thank you for the opportunity to present my work here. My name is Jan Šubiak. I am the postdoctoral researcher at the Center for Astrophysics, Harvard and Smithsonian, and Czech Academy of Sciences. So in this talk, I will be presenting you about new discovery of the object close to the deuterium burning limit. But let me start with the introduction. So we are currently living in the golden era of transiting brown dwarf research, experiencing a recent increase of new transiting brown dwarf discoveries thanks to the TESS space mission. And as you can see in this figure, highlighted by the red circles. So to differentiate between giant planets and brown dwarfs, we are using a deuterium burning process, which primarily depends on the mass of these objects, and generally adopted value is 13 mass of Jupiters. However, this definition also has some intriguing consequences for the objects close to the boundary. So as I will be discussing further. Okay, so let's move on. So TOI 4987b is the recent discovery of the transiting objects close to with the mass close to the deuterium burning limit. And as you can see in the mass radius diagram, its position is quite extraordinary. It has second largest radius in the whole population. So despite the because of the old age of the system is about 2.4 billion years, we would expect to observe radius around 1 radius of Jupiter. So studying and trying to understanding the large inflated radius of the object was a very interesting challenge. So firstly, we focus on the processes which are generally attributed for large radii of many hot giant planets, such as stellar irradiation. So we use thermal evolutionary models, which also include stellar irradiation effect in the modeling. And however, these only produce a slightly larger radius of around 1.1, 1.2 radius of Jupiter. And you can already see in this figure that this effect of star irradiation scaled with the mass, and for the objects as massive as 3 mass of Jupiter, this effect is already quite low. However, it was discussed in the literature that many large hot giant planets, which has the largest radii observed today, cannot be explained by the inflated atmosphere alone, but they need to also have inflated interiors. And there are several mechanisms which are attributed that could dissipate energy to the interior of the planet. Some of them are tidal heating or processes powered by stellar irradiation. So let's first focus on tidal heating. This can be powered, for example, by the eccentricity of the orbit, or by, for example, orbital decay. It was observed in some system of hot Jupiters. However, for this system, we do not expect orbital decay because the rotation period of the star is similar to the orbital period of the companion. However, we detected that the orbit is slightly eccentric, so we indeed expect some energy dissipated to the interior to the tidal heating. On the other hand, dissipated processes powered by star irradiation appear very realistic in this case, and it's because the star recently left the main sequence and become subgiant, which also increased the stellar radiation a lot recently. So we use basically the heating efficiency of about few %, as was discussed in the literature for these processes powered by star irradiation, and we compute that the energy dissipated to the interior is 1 order of magnitude larger than what we get from the tidal heating. However, when we're using the internal structure models and the heating efficiency of this few %, we are getting the radius, predicted radius for these objects around 1.2 radius of Jupiter. Even when we use the hypothetical case of 20% heating efficiency, we are still getting radius of around 1.6 radius of Jupiter barely. So to conclude all this, we indeed expect the energy dissipated to the interior, and we found that the processes powered by star irradiation are dominant processes in this case over the tidal heating. However, they are not sufficient enough to explain the observed radius of this object. However, this energy dissipation would increase recently a lot as the star left the main sequence and become subgiant. So as I told you, the mass of this object is close to this 13 mass of Jupiter, which is boundary for the deuterium burning limit. So we studied the deuterium burning as possible solution for the large radius. And in this plot, you can see several tracks for the deuterium burning in the object of 13 mass of Jupiter's object. And the different colors in this case represent different helium fractions. So this deuterium burning do not only depend on the mass, but also on other parameters like helium fraction or initial deuterium abundance, metallicity, and so on. So, but what I want to show you from these two plots is on the right plot, you can see that despite the old age of this system, it is reasonable to assume that our objects, TOI 4987b, still have a large fraction of its initial deuterium. And on the left plot, when you can see the deuterium luminosity as the fraction of total luminosity, you can still see that even an older age, this deuterium burning is still happening. As the deuterium burning reaction depends strongly on the initial temperature, internal temperature, the idea is that a recent increase in the energy dissipated to the interior as star left the main sequence and become subgiant would also increase the deuterium burning rate in this object. However, we want to also study what would the deuterium burning do with such old, cold and compact object, because usually when we study deuterium burning, it is in young brown dwarfs, which are formed very hot and large. And basically this deuterium is halting for some moment, they're cooling and contraction. However, we can use the objects from via core accretion through cold start as good analog for this object, because this assume this what would deuterium burning do with a cold and compact object. As you can see from these three pictures, that basically deuterium burning would increase luminosity, effective temperature, and radius. So as we know from the mass radius diagram which I showed you, we already know that the radius of these objects is quite large, which is in agreement with deuterium burning. However, we can also luckily study also the effective black body temperature through secondary eclipses detected in test photometry. So we indeed found that effective black body temperature is much larger than equilibrium temperature, it's 3,500 Kelvin compared to 2,000 Kelvin. So this is indeed also in agreement with the deuterium burning. And finally, I want to also show that, say that also the system is very interesting from the composition side, because it's not only there is this brown dwarf orbiting around the primary F-type subgiant, but also there are another two stars in the system. There is one which was detected from the long trend in the radial velocities, and you can see in the lower figure on the right. But also there is another star detected from higher some imaging. Okay, so to conclude, we firstly tried to describe or explain the radius of these objects by typical processes which are associated with large radius of hot giant planets, but this failed to reproduce the large radius of this object. However, because the stars is becoming is subgiant and left domain sequence, so a recent increase in the energy dissipated to the interior, followed by the increase in deuterium burning rate, can be a possible solution. So this would be first object to known to date to burn deuterium in quite old age, while the star is post-sequence phase. And by this definition, it was basically translated from giant planets now to the brown dwarf. So thank you.
Thank you. We have time for one question. The audience or then no question. No questions. So thank you. So the next presentations will be by remote. The next one is Aruna Devi, detection of sulfur cycle in Enceladus using latest technology advancement.
Hi everyone, just presenting my screen. Just give me a second, I'm just sharing my screen.
You are the present.
You able to hear me now?
Yes, okay.
Okay, yep, thank you. Hi everyone, I'm Aruna Devi from International Space University, representing Brahmastra Aerospace and Defense from India. And today I'm going to discuss about the detection of sulfur cycle in Enceladus using latest technological advancements. And to talk about latest technological advancements, everybody is aware of AI. Today, AI plays a very important role in each and every field. And we are going to see how AI could help us in detecting search for life in other planets. Enceladus is our target planet for search of life, which contains all the ingredients for the sources of life, which may be considered even as a future home planet. Search of life beyond Earth is always a curiosity to humans, which could provide paths to discoveries. And today we are going to see how AI is going to help us using the different minerals found in Enceladus, and using which we are going to find what all organisms could be searched or what kind of life to search for in Enceladus. Humans are always very curious about the other planets, and we are just finding ways to get into other planets because we need to find an alternative home planet, as we are utilizing the most of the minerals and nature in our home planet. And this technological advancements will help us to find and explore the universe. Today, our mission is to analyze the elements in Enceladus. Enceladus contains all the important elements which is required for a human life. That is called as the important biomarkers. And AI, using its properties and data sets, how we are going to analyze these minerals and its properties are, and how accurate we are going to get the data using AI is being discussed in this paper. Sulfur is one of the most important and essential element in the life formation. Is found in Enceladus in the hydrothermal vents. Sulfur mainly comes from the volcanic activities, and it can be formed from different biotic and abiotic sources, like weathering of rocks and volcanic activities, and even plants have sulfur, and which which the animals intake and die, and then after they die, the organisms form different sulfides. And also there are a lot of bacteria reacting to sulfur to hydrogen sulfide. These are also all this they are also the extremophiles found containing sulfur. So sulfur is a very essential element in life formation. So the different isotopes of sulfur. Once we find how this sulfur and how the sulfur compounds uh, are being formed, this could provide us a clue to find which kind of life to look for in the hypothermal vents. And for this, we are going to use AI. Artificial intelligence plays a vital role to find a future home planet. And there are large number of organisms in our Earth which are categorized and which the humans know are maintained as a database. And this database, we maintain in which kind of environment, which kind of organisms live. And these data sets are being used, and these data sets in the analog sites have been maintained, and these are very crucial. And when we find the Enceladus data, like for example, hydrogen sulfide is being found in the plumes of Enceladus, and this hydrogen sulfide, the formation of hydrogen sulfide is precise, and how it is formed. Once we know whether it is from a biotic or abiotic source, we could conclude the thing. If it is from a biotic source, then there is some life inside the waters of the ice of the Enceladus. For sample search, first the thing we are going to find the sulfur isotopes. Above the Enceladus ice and on the plumes, we are going to find the sulfur isotopes. So using which we develop certain algorithms and identify the predecessors. The AI plays a main role in this finding the predecessors, and the data sets has been trained using which the analog sites data sets. So once the data sets that has been found in Enceladus and in Earth are compared to each other, and in Earth, there are also sites where extremophiles live. And once we compare and we get the exact data, how the hydrogen sulfide, as example, hydrogen sulfide is produced in Earth is the same, and in that environment, what kind of living organisms exist. This could give a clue to us to find what kind of environments actually to find or search for in Enceladus. And in turn, we could find the new life or the new kind of organisms. I would like to give a sample data, that is the hydrogen sulfide, which is found in the plumes. And the geothermal activity is the main reason for the formation of the hydrogen sulfide, which has been found recently. And this hydrogen sulfide is also found in the moon as well, in our moon as well. And this kind of sulfur activities is taking place in our outer planets as well. And this could give us a clue to the future life. And we could also conclude that what kind of organisms to look for by comparing them with the analog missions. Thank you everyone for giving me this opportunity, and this results and this technology would help us further to find our future home very soon. Thank you.
Thank you very much. And we have some time for some questions from the audience or remotely.
Yeah.
Yes, please.
Thank you. I have a question about how molecules you find and which molecules. Repeat.
There is a question. Are you listening?
No, I'm not able to hear the question. Can you just repeat it again?
Okay. How molecules you find and which molecules?
Molecules, that is what the recently previously Cassini has found that the certain minerals has been discovered from this, and we have to make missions to find what kind of molecules has been what kind of molecules are present in Enceladus ice, over the ice and the plumes. We need to make a mission, and using that data, we need to train our data sets. Thank you.
More questions? If there are no more questions, we move on. And the next presentation is also remote, is by, oh.
Thank you, everyone.
And so the next presentation is by Jack Lissauer, President of Commission F2. He will give his report.
I uploaded a movie file. Do you have that?
Yes, they have it. Okay.
Could you play that, and then I'll be available to answer questions?
Okay, please.
Thank you.
Can go.
The state of Commission F2, exoplanets, and the solar system. This commission was created from the merger. Hi, this is Jack Lissauer. I'm sorry I can't be there with you in person, but I want to give a little bit of a report on the state of Commission F2, exoplanets, and the solar system. This commission was created from the merger of two previous commissions, planets and satellites within the solar system and exoplanets. And although the techniques used to observe exoplanets and solar system planets are quite different, the physical processes and the objects are very similar, and the commission promotes exchange interactions between the two communities. Various areas of scientific activities and expertise that the commission covers, basically planetary science broadly defined. The health of the community is quite strong. Solar system studies remain very strong, continuing advances, including from some major spacecraft. And many countries are now contributing, especially with the Moon and Mars. And exoplanets continues to be one of the most rapidly growing major topics within the whole astronomy astrophysics domain. The commission members participated in the public naming campaign that provided names for more than 100 exoplanets in April of this year. It took a long time to put together. And we reviewed relevant proposals for IAU symposia and focus discussions. Most proposals were of high quality and were endorsed, and some actually have been occurring during this GA. And together with Alain Le Cavalier des Étangs, the previous president of this commission, I published a paper on the history of definitions of a planet, focusing on changes made by the vote of the members of this commission in 2018. This is in New Astronomy Reviews. It's also on archive. And if you're interested in details, by all means, take a look at the paper, because this is a topic that looks like it's going to be coming up a little more. And the current state, the famous IAU definition of planets within our solar system, controversial in some circles, from a resolution at the General Assembly back in 2006. And then there's the working definition of an exoplanet that was created in the early part of the century and most recently amended in that vote I talked about in 2018. But there are things that are outstanding. Exoplanets aren't part of the official IAU definition of planets. There isn't a consensus on the optimal definition of planets. And there's a new proposal by Jean-Luc Margot that you may have heard about already this week on amending the IAU definition. So the role of our commission there is we have the most expertise on planets. And exoplanet working definition was changed in 2018 by a vote open to all members of our commission. And several hundred votes. The organizing committee is discussing what advice we can provide the IAU. Many issues remain. The commission welcomes suggestions, the organizing committee, from commission members and other IAU members. We are going to set up an email and inform members of the commission of how to do that, email and probably a web address where people can provide their comments. Just to get that started, we've talked a little bit about a simple path extending the current solar system definition of planets to exoplanets using the exoplanet working definition. And the two things are to generalize what object from just orbiting the sun to any star, stellar remnant, or brown dwarf. And then because the solar system definition doesn't have any upper limit, it would include binary stars. It would include objects where you have a 14 Jupiter mass object, which is a brown dwarf, orbited by a 12 Jupiter mass object. So there's a mass ratio limit of about 25:1, where there aren't many binaries like that. It's a kind of a valley in the observed distributions. Now this is just the simplest thing, and there are many astronomers who want fundamental changes to the definition. The question is, does any of these change have majority support in the individual change? And the discussions just started. Much remains to be decided. Our commission can provide some advice. Anyway, that's some of my presentation. I hope to be able to join you on Zoom and answer questions in my few remaining minutes. Thank you for your attention.
Thank you, Jack, and for this very nice review. Thus, we have asked a question from the audience. Please go to the mic.
Yes, I wonder if there is a time for pushing for a definition of exoplanet. I think that everybody more or less agrees that the deuterium fusion limit works well, and this is a clear separation between exoplanets and brown dwarfs. But I think that we are still very far from discovering exoplanets small enough in order to have some uncertainty about what they represent, whether minor bodies or planets. I think that for the time being, we don't need really to push ahead trying to go for a definition that we lack enough observations.
Well, I think that's it's a valid position, but this is why the IAU working group on exoplanets put in a working definition. That was over 20 years ago. And we know a lot more about it. And as we find out more and more going down to smaller sizes, there's going to be more ambiguity. And there could be more ambiguity in our solar system if we find something quite large out at several hundred or even several thousand AU. So the question is, in some sense, I think that from researching what's gone on with planet definitions and minor bodies being added and removed in the solar system for centuries, in astronomy, really, this is a science, it's not religion, and therefore all definitions in some sense are working definitions. And it would be better to have a little bit more officialness in the definition, although whether we really want to have extremely detailed definitions of where it's what the lower limit would be, it is, I think, a good question, and how much specificity and versus how much deliberate vagueness, because there really aren't boundaries in nature, or if there are, we don't know about them very much at the lower end. So I think there are good arguments in that side, in both sides, and that's the problem with very many aspects of the definition. I don't think we're going to find anything that's anybody's real preference. I really like Jean-Luc's wording of dynamical dominance as opposed to clearing its zone. I think it's a better concept, but I'm not sure about a particular formula, because if you wanted to have everything included, you have to include stellar evolution and timescales for that, different timescales, whether you include the lifetime of the star, it gets to be somewhat complicated. So specificity versus generality, again, there are pluses and minuses, and that's something that the organizational committee and the new president, Miriam Rengel, will be heading up, and I'll just be there providing my advice as past president. But
Okay,
when we'll send out an email to the entire commission membership and informing of feedback mechanisms, and you're welcome to send some formal feedback. Thanks.
Okay, thank you very much. We have to move on. The next presentation is by William Welsh. What if Earth orbited TRAPPIST-1? It's a question.
Great. Okay, TRAPPIST-1 is a fascinating system with 7 planets that are roughly Earth size, 3 of which are in the habitable zone. So it's natural to ask, could there be life in the TRAPPIST-1 system, and what would life be like, and what would evolution on one of those planets be like? Unfortunately, we don't have anywhere near enough information to do a realistic analysis and answer that question. So it's the end of the road. There's nothing more we can say without being mired in a host of very specific, untestable assumptions. But what we can do is we can ask an analogous question, which is, what if we put the Earth in the place of TRAPPIST-1e? What would happen then? Because we do have information about what happened on Earth, and we can use this hypothetical planet in this hypothetical orbit around TRAPPIST-1 to try and understand what might happen and maybe gain some insight to a problem that's otherwise intractable. So the important things to know are that
the most important thing that happened on Earth since the genesis of life is the rise of oxygenic photosynthesis by cyanobacteria. This occurred about 3 billion years ago. Then it took about 700 million years for oxygen levels to rise from negligible amounts to even a few percent. And 2.3 gigayears ago, we had the Great Oxidation Event. Then it was about 2 billion years past, the boring billion years past, before we get to the Cambrian explosion. And this is the big bang of biology. This is where there's enormous diversification and the origin of all complex multicellular life. So looking at the graph there, I don't have a pointer and people online won't be able to see. But will I see online if I do this? Oh. Well, in any case, basically there was negligible amounts of oxygen in the Earth's atmosphere for almost 2 billion years. Then a huge spike, the Great Oxidation Event, and then plateaued for a while. And then we have the Cambrian explosion near the end. Now, shown here is a spectrum of the sun and TRAPPIST-1e, two spectra of the sun, the current day sun, and then the sun in the Archean age, 2.65 gigayears ago. It's about 20% dimmer. The red spectrum is obviously TRAPPIST-1. The thing I just want to point out is the y-axis is not energy flux, it's photon flux. So we're counting numbers of photons, hence the strange units there. The green part of the diagram is the important part for photosynthesis. This is known as the PAR, photosynthetically active radiation. And this is the light that's used by oxygenic photosynthesis to split the water molecule. The water molecule is the origin of the oxygen. And photons with less energy than this don't carry enough oomph to help split that water molecule. Now, if you look at the sun, about 23% of the sun's photons are in the photosynthetically active region. But if you look at TRAPPIST-1, it's less than 1% solar. So there's a problem here. I mean, if you just look at this, you can quickly make an estimate and say there's going to be very little or no oxygenic photosynthesis on TRAPPIST-1. So you just throw in some numbers and you can say, how long would it take if we took the Earth and scaled the time scale based on simply the number of photons you have to do photosynthesis? How long would it take to have a great oxidation event? And I should say, the reason it took so long on Earth is there are a huge number of oxygen sinks. You have oxygen source, which is the cyanobacteria, but as quickly as it's being produced, it is being removed by geological effects, chemical geochemistry. So it took a long time for oxygen levels to build up. If you just scale that to TRAPPIST-1, it takes 77 gigayears or 63 if you want to use the linear approximation for the Archean sun. Enormous amount of time. But this is a terrible approximation. The linear approximation is terrible, and there are some forms of cyanobacteria that can extend the PAR a little bit. So what I'm showing here is curves for different species of cyanobacteria and the amount of oxygen production on the y-axis. This has all been scaled because different bacteria have different levels of oxygen production. So I just scaled the peaks to 1. And on the x-axis is how much irradiance they get, how much light they're getting, how much light they're receiving. 800 on this scale is about the average Earth amount. 650 is the Archean Earth. The dotted line way on the left edge, that's the amount you get from TRAPPIST-1. So the important thing about this figure is this is not linear at all. The amount of photosynthesis increases and then it plateaus or peaks and then drops off. So at high light levels, plants, cyanobacteria, they just don't like it to be too bright. They prefer low light levels. And so you have to include this into account. The second thing you need to include is there's some cyanobacteria that can use chlorophylls D and F. So most plants use chlorophyll A and B. Kelp and algae use chlorophyll C. Cyanobacteria can use D and F. They can extend the PAR by 50 nanometers. So you go from 400 to 750 nanometers. Not a big deal on Earth. It extends the amount of energy, the number of photons you get by about 16%. But on TRAPPIST-1, it actually doubles the number of photons. So that 50 nanometers doubles the number of photons in the PAR. So it's hugely important. So you got to include this extended region. So you put this together, you use all the different species you can come up with, and you get this range estimate for how long it would take to get to a great oxidation event. And it's roughly between 1.8 and 15 gigayears. That spread is due to the vast spread in the number of different species and the way they operate. But we do have a best one here. This is based on a cyanobacteria that grows at low light levels, which is what you expect, and uses chlorophyll D, which is what you need to make the best use of the light that you have. Nevertheless, it would take a very long time to get to the Cambrian explosion. The age of the system is about 7.5 gigayears, so you wouldn't expect that. But you would draw the wrong conclusion if you ended here. And the reason for that is oxygenic photosynthesis is only one type of photosynthesis. There is non-oxygenic photosynthesis, and there are many different forms of non-oxygenic photosynthesis, and it evolved earlier than oxygenic photosynthesis. The important thing is non-oxygenic photosynthesis does not split water. It splits hydrogen sulfide and other sulfides, other hydrogen hydrogen-bearing molecules. And you split those molecules, you don't need as much energy. You can use photons out to 1.1 microns. So then if you look at the spectrum out at 1.1 microns, you have an enormous amount of photons there. You have 22 times more photons available if you do non-oxygenic photosynthesis than if you do oxygenic. So non-oxygenic photosynthesis, we predict, will completely dominate. So the conclusions are here. Anoxic or non-oxygenic photosynthesis, because of its huge advantage, will dominate. Completely dominate over the cyanobacteria. The cyanobacteria is the only genus that really evolved oxygenic photosynthesis, and the plants came from that. Hence, if there's non-oxygenic photosynthesis dominating, you will never get a great oxidation event. You will never get a Cambrian explosion. You should not expect complex animals or any complex multicellular life on a planet orbiting any one of these late M stars. TRAPPIST-1e was just a good analogy so we can get specific numbers, but the results hold in general. With that, thanks for your attention.
Thank you very much. We have time for a question. Please go to the mic.
Quite cool thought experiment. Just a question, is it unthinkable that a Cambrian explosion could happen on anoxygenic from bacteria or from anoxygenic life?
I don't think so, because oxygen is a highly reactive molecule. It's basically toxic to many forms of life. It's so powerful, it provides a factor of 15 times more energy, or roughly. So using oxygen really gives you an enormous advantage. If you don't have oxygen, you're limited to low energy life, which then means you will have multicellularity, but you might not have complex animal life. That's my guess.
Okay, thanks.
More questions? If not, we thank presenter. And so we go to the last presentation is by Ronald Lopez, the development of a superconducting MKID high-resolution multi-object spectrometer test bed for the detection and characterization of exoplanets. Long. Please.
But thank you everybody for sticking around to the end. This talk is going to be a bit different from the other talks. I'm going to be talking about a test bed for a new type of spectrograph, an MKID high-resolution multi-object spectrograph. And so first I'm going to begin with a little overview on the difference between a high-resolution and multi-object spectrographs. And so first, the shell spectrographs or high-resolution spectrographs, these are primarily used to look at a limited field of view, like one target or a target in a slit. And you want to see a high resolution, high dispersion spectra from this thing. And so the way we do that is use these shell gratings with high spectral dispersion. And when you look at high spectral dispersion, you actually get a lot of orders that overlap. And so you need to separate out those orders so that you can actually understand what you're looking at. And so that is done with a second dispersive element or a cross disperser. And you end up imaging multiple orders of your spectrum on one detector. And so this is an example from Keck NearSpec. This is what some high resolution spectra data will look like. And you would trace along these rows to get your spectrum. Multi-object spectrographs, on the other hand, are aimed at looking at multiple objects. And so instead of having multiple orders, you usually look at a more limited spectral range and usually at lower resolution so that you can actually fit multiple spectra on your detector. And this is also true about integral field spectrographs, which is a kind of a type of multi-object spectrograph. But instead of looking at multiple slits, you might be looking at a field, and each little chunk of that field you look at the spectra of. And so in both cases, your detector space is being taken up by different objects or different areas of your field of view. In general, in direct imaging, high contrast imaging, integral field spectrographs with lower resolutions are used to find exoplanets. So we can use the spectral information to better remove the stellar PSF, which allows you to see dimmer planets next to really bright stars. But you can't really get a lot of information about the planets themselves. But if you can find them and locate them, then you can follow up by using high resolution spectrographs, where if you know where the planet is, you can place a fiber where it is and send that light, that isolated light, into a high resolution spectrograph, where you can then look at the high resolution spectra and look for atmospheric signatures and things like that. And so in general, the integral field spectrographs are used to find, and high resolution spectrographs are used to characterize in direct imaging. And so in both cases, you are limited by this detector space. You either have high resolution and you can look at a few things, or you have multi-object and you can, so you can look at a lot of things, but then you're limited in space, in spectral resolution. However, these new devices called MKIDs, microwave kinetic inductance detectors, don't have that same problem. And that's because these are superconducting detectors, which means that they are photon counting at microsecond timescale, so they can tell you the arrival time of each photon. And they have no read noise, and they're energy resolving, which is not shared with most used detectors. And so a brief overview of how they work. So they're superconductors, and so when a photon hits them, it breaks Cooper pairs, and that breaking of Cooper pairs changes the inductance of the superconductor. Now, if you have an inductor and a capacitor in a circuit together, they create a resonant resonance and a resonator, I should say, with a characteristic frequency and phase. And by changing that inductance, you then change the characteristic frequency and phase. And you can measure these shifts in order to determine something about the photon. And so here's an example of what a single pixel might see. So as time goes on, you get these pulses. The location of these peaks in phase will tell you the arrival time of the photon, and the height of the phase will give you the energy. And so you can actually use these to do really cool things. And the thing that I'm interested in using it for is using this detector space more efficiently. And so, as I said before, for high resolution spectra, you need to take up all of this detector space in order to get this spectral information. But if a detector can determine the wavelength of a light, then you can actually use the detector to tell the difference between this light from this order, light from this order, light from that order. If the MKIT itself could have a really high spectral resolution, you could just let it get light and it can tell you the wavelength of everything, but you can't get up to resolutions of like 100,000 or 50,000 with the MKIDs alone. But instead you can use them instead of that second cross disperser and collapse this information into one row of pixels. And so we no longer need a 4 megapixel camera to get this information. You can do it with just one row of 2000 pixels or larger if you'd like. But that allows us to do really cool things. So now if you decide to look at a star, you can have a bundle of fibers and you can sample the region around a star. And if each fiber can give you high resolution spectra, that means you can get high resolution spectra from each one of these fibers. So now you're getting the power of a high resolution spectrograph, but per fiber. And if there happens to be a planet, let's say, that's around your star, and you sample this region, then one of your spectra will have slightly different signature than, let's say, the ones on the star, the background. And you can use that information to both find exoplanets and characterize them simultaneously instead of needing to follow up. And so with an instrument like this, you can both find and characterize exoplanets and get information about the rate of velocity, spin, atmospheric parameters, and things like that with a facility class instrument. Now, this, like I said, is a test bed. And so we are currently working on this at the University of California, Santa Barbara. And so here's our test bed. You can ask me after if you have questions about it. And we are currently, it's assembled. We are currently taking data now. And so we'll have our first preliminary tests of this soon. And I just want to end with this. So I want to give a shout out to Crystal Kim, who did a lot of the work we have a simulator. Oops, sorry. We have a simulator that takes some input spectrum and convolves it and broadens it, but it convolves it with the Blaze function of the spectrograph, and then creates a photon table, which is what MKIDs produce, and that tell you the photon energy, the arrival time, and the pixel that it hit, and creates these photon tables, which then you can see how an MKID would actually look at real data. And then also the reduction pipeline, which is kind of the inverse, where it takes a photon table as if that were the data that you had collected, and then turns it back into a spectrum. And so that paper was just submitted as of like 2 days ago, so look out for that. And so I'll just leave you with my key takeaways and take any questions. Thank you.
Time for a short question on the web. No? Okay. Thanks again.
Thank you.
So we are at the end of our division day. I like to thank all the participants, all the speakers, and just like to say that the new president is Athena Kustenis. So it's very important the participation of all the members for the development of all discussion, everything. So please be active and participate to general discussion of the commission, the division. Thanks again to everybody. Huh?